They contain four bond pair of electrons and they contain one electron pair. So now again we'll look into a case which has five electron pairs. So the total number of electron pairs is five, but here three are bond pairs and two are lone pairs. So you see, so when the electron pairs is five, total electron pair is five, it should be TBP shape. But here in this case, three bond pairs are present and two lone pairs are present. So what happens, instead of the actual TBP shape, because of the presence of two lone pairs, the shape now changes to T-shaped. Now here it has been shown in this figure how does a T shape look like, and the common examples of molecules which are T-shaped in nature is ClF3, BrF3. So similarly, we'll again consider a case where the total electron number is 5, but in this case the number of bond pairs is 2 and the number of lone pairs is 3. So here in this case, the geometry of the molecule, it becomes linear. Here you can see in this case, and the examples are ICl2 minus and xenon difluoride. So here you can see, even if the total number of electron pairs is 5, the difference in the bond pairs and the lone pairs, they ultimately predict the geometry of the molecule. So similarly, if we look into the case 6, that is, we'll consider the case where the total number of electron pairs is 6, and if there is no lone pair, then it is the regular case of a octahedron, that is sulfur hexafluoride. We know that it is a regular octahedral geometry. Then now suppose we will consider one case where there are five bond pairs and there is one lone pair. Then instead of acquiring the original octahedral shape, then the molecule, it acquires a square pyramidal shape. You can see here in this figure, and the common example is IF5 and sp5f2. So similarly again, for electron number 6, if we have total electron numbers counting to 6, if there are 4 bond pairs and 2 lone pairs, even if the electron counting number electron pairs is 6, the geometry of the molecule changes to square planar because of the presence of 2 lone pairs of electrons. Now here this is how the geometry it looks like, and the common example for this square planar complexes, for this square planar molecule, is xenon tetrafluoride, so XeF4. So this is how the Vesper theory, it talks about the importance of the mutual electronic interactions which predict the geometry of the molecule. So now we should understand how we can apply the Vesper model systematically to understand the different shapes of the geometry of the molecule. So first, to determine or to predict the geometry of a molecule, first we will write the electronic configuration of the elements, or we will write the Lewis structure. Like, we'll take a simple example, that is carbon dioxide molecule. So here in carbon dioxide molecule, there are total 16 valence electron and it will be distributed among the three atoms, that is two oxygen atom and one carbon atom. So this is how it looks like. In figure 2.1a and b, you can see the Lewis structure of the carbon dioxide molecules, and we can see that the distribution of the valence electrons has been done. So then we should note here, the in both these cases, that is, if you look carefully, both the structures A and B, they are valid structures, and they, but even if they are valid structures, we cannot actually predict the bond angle from the Lewis structure, because in figure A you can see it is a linear molecule, whereas in figure B you can see it is a having a 90-degree molecule. So among these two structures, which is the actual geometry for carbon dioxide, that we will predict according to Vesper model. So now a structure should be considered which lets all the electron pairs in the valence shell of the central atom to go as far as possible. So this helps the molecule. So once we take the electrons that are far apart from each other, if the electron pairs, they are far apart from each other, then overall energy of the molecule, it is minimum. So that is why we will always try to look into the geometry which gives us the minimum energy for the molecule. So here we will, for any molecule, if we want to predict the geometry of any molecule, the we will first, after uh, arranging the valence shell electrons, we will always look into the structure where the electron pairs, they are far away from each other. Because the more the distance between the electron pairs, then higher is the repulsion, and we see that the system achieves the lowest energy. So here some of the this helps the molecule to achieve the lowest energy, and we can predict which basic shape the molecule can adopt by the relation. Then we will look into the basic relation between the number of the electron pairs and and the arrangement of the molecules that we have studied before. So here, so if the shapes are looking, we have to find out which location corresponds to the atoms, and then we will predict the shape of the molecule. So here, when we say carbon dioxide, here in carbon dioxide, it is a linear molecule. Water is a bent molecule. Like bent molecule means that it has an angular structure, or what we call it as the V shape. Then boron trifluoride is trigonal planar. Ammonia is trigonal pyramidal. Then we have methane tetrahedral, and some of the examples here it has been given. Now sigma and pi bonds, they are dealt by ignoring the sigma bonds at first. Like for example, in carbon dioxide we see two sigma bonds, they are formed on opposite sides of the carbon atom. Now what hybridization of the carbon, that is 2s and 2pz, they give the s orbitals with a bond angle of 180 degree. So first, we will look into the formation of the sigma bond, then we will look into the formation of the pi bond. Then the third step, it comes on deciding on the number of the sigma bonds. Next, pi bonds are added so that the molecule gets completed. That is, we will first look in, write the electronic configuration, that is the valence shell electronic configuration. Then among all the predicted geometry, we will try to find out where is there is minimum repulsion. Then we will look into the sigma bonds first, the formation of the sigma bonds, and in the second case we will then, after we have looked into the uh, formation of the sigma bonds, then we will add up the pi bonds, and then finally we will see the geometry of the molecule. So here some simple molecular structure in which all electrons on the central atom form bonding pairs. Like here in trimethyl borane, you can see this is in figure A, this is trimethyl borane. The second is carbonyl chloride, that is COCl2. Then phosphorus, here in figure C we have phosphorus oxyfluoride. In D, phosphorus pentachloride. It is figure E is phosphorus tetrachloride, and in F is, it is a dimer, that is aluminium bromide dimer, it has been shown. So the molecular orbital, they approach the mostly the MOT theory. It is the most accepted theory to justify the structures of different types of molecules, or to justify the geometry of the different types of molecules. But the Vesper rules, it can also be applied directly, and it is much easier to predict the geometry of the molecules. So let us predict the structures of some inorganic compounds after drawing their Lewis structure and applying the Vesper rules. So first, we will try the case of trimethyl borane. So, trimethyl borane is CH3 whole 3p. So, according to the Lewis structure of trimethyl borane, we will place 6 electrons in the valence shell.
Hmm. अंक काढो
Please switch off your microphone.
बिजी म्हणते
Okay. So, we were talking about trimethyl borane. Trimethyl borane is CH3 whole 3b. So here we will place the 6 electrons in the valence shell of the boron atom. So to minimize the repulsion, the methyl groups, it should be located at the corners of the equilateral triangle. So as a result, we see a sp2 hybridization for the boron atom. So then this is how once we see the sp3 hybridization, and then we see the formation of the equilateral triangle. Then phosgene is COCl2. It has 8 electrons about the carbon, but one pair it forms the pi bond and the of the double bond. So sp2 hybridization will be more stable. So here in figure 2.2b phosgene, here it has been shown two pi bonds, they have been formed here. Then phosphorus oxyfluoride. So first we'll draw the Lewis structure of phosphorus oxyfluoride, that is POF3. So here it has been shown in figure A and B, the two possible Lewis structures of POF3. Then so here the sigma bonds they for from the sp3 tetrahedral orbitals they form between the phosphorus atom and each of the three fluorine atoms and one oxygen atom. So the symmetry here, this is given the phosphorus. If you see, this is the in figure C, you can see how the overlap it occurs. This is POF3, here it has been shown here. Then the symmetry gives a fifth bond, that is the d pi p pi bond, which is formed by overlap of the 3d orbital of the phosphorus with the 2p orbital of the oxygen. So the symmetry here we get is C3b.2. Then phosphorus pentachloride, that is PCl5. So PCl5 molecule, it requires 10 electrons in its valence shell of the phosphorus, which forms 5 sigma bonds. The 5 sigma bonds, they can be oriented in such a way that they are equidistant from one another. So once this arrangement, it gives rise to the trigonal bipyramidal and square pyramidal arrangements. They both, to since we have 5 sigma bonds, so the TBP and the square pyramidal arrangement, they both can be applied. Now other than coordination compounds, most of the 5 coordinate molecule, they form the TBP structure. So here if you look here in this figure 5, this is the structure of the phosphorus pentachloride. So phosphorus pentachloride, so the bonds are of two types. One is the axial bond and the other is the equatorial bond of the three p bonds forming a trigonal plane. So the structure of PCl5 here, it's mostly TBP. Then is aluminium dibromide. It is a dimer. So we expect a trigonal planar structure with 120 degree for the molecule AlBr3. But when the AlBr3 molecule, it was looked in experimentally with the X-ray data, it was found that AlBl3 does not exist as a monomer. It exists as a dimer, that is Al2Br6. Now this dimer Al2Br6, it contains 4 bonds per aluminium atom. Now this happens as the aluminium, it behaves like an Lewis acids and it accepts a lone pair. So and keeps it in its unused p orbital. So the structure of Al2Br3, you can see here it has been shown the dimer, it has been shown, and the bond angle is 90 degree. So this is how we can predict the different types of geometries of molecules. Now when there are 5 electron pairs around the central metal atom like InCl5 2 minus, where the square pyramidal has very little energy than that of the tri TBP, then both the square pyramidal as well as the TBP arrangement may occur. So this is a typical I indium pentachloride. So what happens here is both this here we see it has 5 electron pairs around the central metal, that is the indium. So here also in this case, since 5 electron pairs are there, so it might have a square pyramidal or TBP geometry. But in for particularly for this molecule, the square pyramidal has only very little extra energy than that of the TBP structure. So that is why both the square pyramidal as well as the TBP structure may also occur for this type of molecules. So various types of molecular geometries we have also talked before. Though the valence bond theory, it has been incorporated in the above examples, Vesper method of predicting structures, that is mostly for the second postulate, that is considering the electronic repulsion, is mostly important. The Vesper hybridization schemes may be avoided for Vesper, but also it is very important in valence bond concept. Although this Vesper has its limitations, it is a very extremely important method for predicting the geometries of different types of molecules. Although Vesper theory has its flaws, still it is one of the very important theories that helps us in predicting the structure of different types of molecules. Then now coming to structure of molecules which contains lone pair of electrons. So here we will specifically look at the molecules that contain unshared electron pairs. So we'll have to look between the understand the difference between the bonding pairs and also the lone pairs and the non-bonding electrons. So this is very crucial when we talk of predicting the geometry of molecules. Bonding, apart from lone pairs, bonding and non-bonding electrons are also important. So to understand this, we'll take an example of water. So water molecule, we know the central is the oxygen atom, central atom is the oxygen atom, and it is bound to two hydrogen atoms and also contains two pairs of non-bonding electrons. So therefore, overall, this oxygen has four pairs of electrons, that is two bonding pairs which is bound with the hydrogen and two non-bonding pairs. So each of these four pairs, now total number of electron pairs, here it becomes four. So each of these four electron pairs, they will occupy the four corners of the electron. That is, the two bonding and the two non-bonding pair will occupy the four corners of the tetrahedron. The repulsive forces, we know that lone pair interaction is greater than lone pair bond pair, and the bond pair repulsion, they now come into play and they ultimately decide the geometry of the water molecule. Then because of the presence of two bond pairs and two non-bonding electron pairs, water molecule, it becomes, which should have been tetrahedral because the total number of electrons is 4, now it acquires a bent shape and not a tetrahedral shape. So the HOH bond angle in water is 104 degrees and 5 minutes. It is sometimes, because it is also less than that of NH, the tetrahedron, regular tetrahedron in ammonia. So why it is less than, the bond angle is less than in ammonia? It is because in water we have two non-bonding electron pairs, but whereas in ammonia there is only the one non-bonding electron pair is present. So this is how we see that whenever a non-bonding electron pair is present, how it influences the shape of the molecule. So now we have learned from Vesper theory that lone pair repulsion is greater than lone pair bond pair repulsion, and which in turn is greater than bond pair repulsion. So as the lone pair, it does not have a second nucleus, it is only attracted to its own nucleus and therefore it occupies a greater angular volume. So here, as shown in figure 2.5, we see four equivalent bonding pairs. Here in this figure A, it represents four equivalent bonding pairs, but in figure B, it represents three bonding electron pairs which is repelled by a non-bonding electron pair. So the angular volume of a lone pair electron, it is greater in comparison to the bond pair, and that is why the in the molecular structure of methane, you see the bond angle is 109 degrees 5 minute. For ammonia, it is 107 degrees, and for water which contains two lone pair of electrons, then it is 104.5 degrees. So as the number of the lone pair of the it increases in the molecule, then the angular volume also, the angular volume of the lone pair also increases, and therefore the bond angle is affected. So here in we have three, the isoelectronic series, that is methane, we have no lone pairs, the bond angle is 109 degrees and 5 minutes. For ammonium, there is one lone pair, so the bond angle is 107 degree. And for water, that is, it has two lone pairs, so the bond angle is 104.5 degrees. So this is how we can see the influence of the number of lone pairs on the geometry of the molecule. So if we follow the second postulate of Vesper, we can state that the lone pair will always occupy a greater volume than the bond pair of electrons. The approximate molecular shape along with the possible distortions, they can be predicted only if we consider the lone pair. So now we will predict the structure, how to perfectly predict the structure of the molecules considering both the bond pairs and the lone pairs. So first here we'll take the example of sulfur tetrafluoride, that is SF4. So when we look into SF4, it has 10 electrons in the valence shell of sulfur, out of which there are four bonding pairs and one that is non-bonding pair. So that is total five electron pairs are present, and out of which one is non-bonding and the other is the four bonding pairs. So if the total number of electron pair here, it is five. So as per Vesper theory, the geometry should be trigonal bipyramidal. Now we will take the particularly focus on the lone pair and try to predict the geometry, the actual geometry of the molecule. So we have this lone pair, there is only one lone pair present in the molecule. So there are two possibilities of arranging the lone pair. Either we can place it equatorially or we can place it in the axial position. So now when the lone pair is placed in the equatorial position, it is actually found to match with that of the XRD data. Like here it has been shown here, when the lone pair is placed in the equatorial position, then the bond pairs are repelled by the lone pair, and then as a result, because of the presence of the lone pair here at this position, equatorial position, then the bond pair that lies close to this lone pair, they, what happens, they are repelled and they are pushed back and they form a distorted TBP structure, which is called as the seesaw structure. So this is how we see the presence of lone pair. It distorts the original TBP structure of the SF4 molecule, which now occupies a new shape, and that geometry is called as seesaw geometry. Here it has been shown here. Now here, if we look into figure 2.7a, we see that the lone pair has 390-degree interactions with the equatorial bond pairs, but only 290-degree interactions with the axial bond pairs. So the 120-degree interactions, they are not important to decide the structure. So what decides the structure is the repulsive forces that this lone pair it exerts on the bond pairs. So for all cases, lone pair always adopts position which minimizes the 90-degree interactions. So when it minimizes the interaction, the two bond pairs which are present in at the equatorial position with the lone pair, then we push back and then we get a seesaw structure. Then again we will look into dichloroiodate ion, that is ICl2 minus ion. So this ion, it has two bond pairs and three lone pairs. So here the number of a total number of electrons is 3 plus 2 electron pairs is 3 plus 2, that is 5. So as per our theory, this molecule it should occupy a TPP structure. Then but because we have three lone pairs, we have two bonding pairs and three lone pairs. Now due to the presence of the three lone pairs, the geometry of the ICl2 minus is changed. The three lone pairs, they occupy the three equatorial positions to minimize the repulsion and avoid distortion here, as it has been shown here. So this says I has 7 electrons plus 2 electrons from the Cl plus 1 electronic charge, that is 10 electrons, now which gives us the 5 electrons, and ultimately it occupies a linear geometry. Now here it has been shown. Then again, another case is pentafluorotellurate ion, that is TeF5 minus. It has the tellurium ion, it has the 12 electrons, that is 6 pairs in its valence shell. So the 5 bond pairs and 1 lone pair of electrons, they form the octahedron, as here it has been shown. In this molecule, 1 lone pair is present and 5 bond pair is present. But when experimentally, that is the XRD data, it showed a different structure. Then when the interaction or the effect of lone pair was considered, then it was shown that this molecule, it occupies a square pyramidal structure with the tellurium atom lying in this place. So here this is the tellurium atom, and this is the predicted geometry was, it should be square pyramidal. The predicted geometry was found to be total, it should have been an octahedron, whereas due to the presence of this one lone pair, the shape now changes from an octahedron to a square pyramidal. So this is how our Vesper theory on the influence of the lone pair interaction has been very crucial in understanding the geometry of the molecule. So one more example has been given here, that is for phosphorus trihalides. So for bond angle in PCl3 molecule, that sorry, phosphorus trihalide molecule is, for PF3 it is 97.7, for PCl3 it increases to 100, for PBr3 it is 101, and for PI3 it is 102. So when we look into this trend, we see that when the more electronegative fluorine atom, it attracts the bonding electron pairs away from the phosphorus nucleus and allows the lone pair to expand. So as a result, the FPF angle, it decreases. So we know that fluorine is the most electronegative element. So when it attaches to the phosphorus atom, then it pulls the bonding pairs away from the phosphorus. So because it pulls the bonding pair away from the phosphorus, then the FPF bond, that is the bond angle, it decreases. So when we see that when a more electronegative substituent is added, then the bond angle, it decreases. Also in the same line, we can say NF3, NH3, OF2 and OH2. So here it also have the same between the two fluorides of nitrogen, and also for OF2 and OH2. So this is how the electronegativity is related to the bond angle of molecules. Then carbonyl fluoride, that is COF2. So here we see oxygen and fluorine, we know they are present in this molecule, and we know that the electronegativity of oxygen and fluorine, they are almost similar to each other. Also, there are, if we look here on this molecule, that is COF2, there is no lone pairs on the carbon atom. That is carbon, we know 4 electrons, oxygen 1 electrons, and 2F, that is 2 electrons. So 3 pairs of electrons are there, and the pi bond is there. So the predicted geometry of the molecule is planar. Though it is planar, but the geometry is distorted from a symmetrical trigonal arrangement. So here it has been shown the geometry, it distorts. The oxygen is doubly bonded to carbon, and the CO bond length is less than that of the CF, because we know that fluorine is more electronegative than oxygen, and that is why the CF bond length, it is less than that, the CO bond length is less than that of CF, giving rise to more van der Waals repulsion for the oxygen atom. So more important is the present case that the double bond contains 2 pair of electrons, so it will require more spacing than the bonding pair. So this is the possible structure of OCF2 and the corresponding bond angles. The A should have been the possible structure, but when we look into figure B, because of the presence of the lone pairs and the bond pairs, and because considering the electronegativity of both fluorine and oxygen, this is the actual structure and the bond angle of the molecule. So also this type of behavior is also seen in compounds with double bonds. Like suppose we take the molecule OSF4 molecule. The doubly bonded oxygen atom, it occupies the equatorial position, thereby binding the fluorine atoms to other equatorial positions here, like it has shown here in figure 2.11b. Other examples, it has been listed the different bond angles in molecule, it has been shown. Suppose molecules that contain doubly bonded oxygen, that is OCF2, the bond angle is 108 degree. Then for O to S2 it is 96 degrees, and this is how it has been reported. Then let us apply the Vesper model to the molecular structure of xenon hexafluoride. So the Vesper model predicts, according to this theory, xenon for the molecule, particularly XCF6, that is xenon hexafluoride, there are 6 bonding pairs and 1 lone pair. That is, which means, so if we consider the total number of electrons, that is 14, and total number of electron pairs is 7. That is 7 pairs of electrons for this particular molecule. So once we have a 7 electron pair, then we see that it has to be a 7 coordinated molecule. But it was predicted that there may be 3 possibilities for xenon hexafluoride. First is a distorted pentagonal bipyramidal, a distorted octahedral, or a distorted trigonal prismatic structure. So these 3 shapes were initially predicted for the xenon hexafluoride molecule. Then the position of the lone pair was then taken into account. The lone pair, it should occupy a definite geometric position and a volume as great or greater than that of a bonding pair. We know that the lone pair, the angular volume of lone pair is very high. So that is why the lone pair should always be given a proper geometric position. 3 other neutral fluorides, that is IF7, rhenium heptafluoride, osmium heptafluoride with 7 bonding pairs are also known. So all 3 molecules, they have d5 symmetry, and the structure for such type of molecules, that is for iodine heptafluoride, here it has been is a distorted pentagonal bipyramid. So this is how we will predict the structure of IF7. Then we were talking of XCF6, which also has 7 electron pairs. It then, based on this observation, so XCF6 molecule was first predicted to have a distorted octahedron, but the lone pair, it was found that particularly in this case the lone pair, it occupied less space than the bonding pairs. Now to understand why, we have always known that lone pair occupies more space, that is the angular volume of lone pairs is always greater than that of the bonding pairs. So in this case particularly, that is xenon hexafluoride, the lone pair was found to occupy less space than that of the bonding pair. So to predict the geometry, 2 possible structures were given. In, that is in figure 2.13, you can see this is the best solution to its structure, which is to be a distorted octahedron in which the lone pair, it extends through a face or through an edge. That is, if you here you can see in this figure A, the lone pair here, it is emerging face of it, it extends through the face of the octahedron. But here in this figure B, you see the lone pair, it emerges out of the edge of the octahedron. So these 2 possible molecular structures for xenon hexafluoride, they were predicted. Now several conformations of this molecule, it was found in either of the 2 molecules. If we look into these 2 possible conformations, the XCF bonds, that is the xenon and fluorine bonds near the lone pair, they appear to be lengthened and they were found to be distorted away from the core. But this distortion is less than what was predicted on the Vesper model. Even other hexafluorides, that is sulfur hexafluoride, UF6, they are perfectly octahedral in nature. Now the prediction of this XCF6 was successful in explaining this distortion, and we can ultimately say that the XCF6 was distorted octahedron. Then the Raman spectroscopy, it was performed, and it further, the XCFC molecule, the structure, it was from the Raman spectra. It was found that it is isoelectronic with XeF5 plus cation, which is isoelectronic and isostructural with IF5. So ultimately, the Raman spectroscopy and infrared spectroscopy, they confirmed the structure of the xenon hexafluoride. Then alkaline halide molecules like MS2, they exist only in the gas phase. So solids ionite like calcium fluoride, most of them, but some are strontium fluoride and barium fluoride. They are bent in nature, so electrostatic repulsion of the negative anions should also favor a 180-degree bond angle. At present, there is no simple explanation of these difficulties, but mostly this phenomena has been explained by Walsh diagrams. So the some important points that we should remember about Vesper theory is that when lone pairs are present, the bond angles are smaller than that is predicted by rule 1. The lone pairs, they always choose the largest side, that is the equatorial position in trigonal bipyramidal case. If all sides are equal, the lone pair always try to remain in transposition to each other. The double bonds, they always occupy more space than single bonds, and if the central atom is in the third or below in the periodic table, the lone pair, it will occupy a stereochemically inactive s orbital, and the bonding will be through the p orbitals and near 90-degree bond angles if the substituent electronegativity is almost of the value of the 2.5. Though the Vesper model has been well received, it is not accurate and it is still not undisputed. So we have since this Vesper theory forms the basis of understanding the geometries, this the theory, although it is flawed, it is still accepted. So now we'll start with the Walsh diagram. So we'll just take a break of 5 minutes, then again join. So we'll start with Walsh diagram. So Walsh diagram for triatomic and pentatomic molecules and also for the d pi p pi bonds. Now, the modification of LCAO-MO methods, that is linear combination of atomic orbitals and the molecular orbital methods, so that the geometry of the molecules can be predicted in a better way, was first it was made easier through the Walsh diagrams. So the Walsh diagram is one of the basis methods which correlates the changes in energies of the molecular orbitals between a reference geometry. That is, firstly, when we take a reference geometry, it should have high symmetry and a deformed structure which should always have a lower symmetry. So like for the molecule BeH2, here it has been shown in figure 2.14, BeH2. So we'll look at the energies of the bonding, non-bonding and anti-bonding orbitals in it. Since the molecule it is bent in nature, the first 2 sigma g orbital is constructed from the wave functions that are symmetric. We know that is the symmetric wave functions are g, that is Girard, and hence on bending there is an increase in the overlap. So the energy of the 2 sigma g orbital it decreases it slowly. So in contrast, when we consider the energy of 1 sigma u, that is the 1 sigma un-Girard orbital, then it increases on bending. We know this is unsymmetrical and it is written as 1 sigma u and it increases on bending. So because the wave function it changes, here the sign has been changed. Here we can see the shading, the change in sign has been represented by shading. The hydrogen overlaps in such a way that the wave becomes negative. Moreover, we know that the linear p is orbital, the linear p orbital it, in the bent molecule it makes less overlap with the hydrogen atoms, thus the energy of the 1 sigma u orbital it increases. Now the BeH2 molecule orbital electron it has this electronic configuration. So because the one that is the sigma un-Girard orbital it loses more electron than the sigma Girard orbital gains, so the BeH2 orbital become it is the BeH2 it is linear and it is not bent. But there are certain limitations for this Walsh diagram. It is accurate only for molecules in which there is a large separation between the NS and NP energy levels. If the NS NP separation is very small, then the 1 sigma u level it does not rise as rapidly as the 2 sigma g falls, and thus the molecule may not be stabilized on bending. So like in MF2 type of molecules, the 3 sigma g and 1 sigma u are unoccupied. So here we will look into the structure and hybridization of some selected molecules. So many hybridizations are not possible for higher coordination numbers. So the possible structures may be classified in the coordination number of the central atom and the symmetry of the resulting molecule. So here, if there are two groups about a central atom, it will form angular or linear molecules. So when three groups are there, it will form pyramidal or trigonal planar molecules. When four groups are there, it will form tetrahedral or square planar. And five groups generally form trigonal bipyramidal, that is TBP, or sometimes a square pyramidal or both. But when we have there are, that is with six groups, then we know it forms octahedral, that is D2sp3 forms. Stereochemically active lone pairs, they additionally we know they lower the symmetry. For example, in BF3 and F3 also we know learn that the hybridization of the lone pairs will be different from that of the bonding pairs. So not all hybrid orbitals they are identical in composition, as they have different percentages of s and p character which are oriented in space. For trigonal bipyramidal there are three strong equatorial bonds and two weaker axial bonds. The square pyramidal hybridization it is dsp2 plus the pz orbital. So also in the trigonal bipyramidal the lengths are different. So the relation between hybridization and bond angle is simple when we consider sp orbital. So for two or more other orbitals, then the percentage of s or p character is given by cos theta is equal to s by s minus 1, or this is equal to p minus 1 by p. So this is how we will calculate the percentage of the s character or the percentage of the p character that is present. So in table 2.5, we will see the different types of atomic orbitals that are involved. So when we have sp, sp2 or sp3, that is, we see one is s and any another p is taken. For dsp2 hybridization, it is d x square minus y square mostly, and then x, the rest two p orbitals are from the px or and the py. When we have dsp3, that is the for tbp geometry, then the orbital here that is involved is dz square s, and p is px plus py plus pz. For dsp3, when it is a square planar configuration, then the dx square minus y square orbital is involved, then s plus the 3p orbitals. And particularly when we have d2sp3, so here, this is, here it is octahedral structure, and the both the orbitals involved are, that is d2, it implies both the orbitals, that is dx square minus y square and dz square plus s and the 3p orbitals. So this is given by table uh, 3.2.5, you can see. So for example, in sp3d set, we see the set of hybrid orbitals into the subset can be resolved into, we have sp2, and the we will break the sp3d hybrid orbital set into sp2 subset and dp subset. So if we take the case of water molecules, the bonding orbitals, they are in pure p and sp3 hybrids. So now we will apply this equation, this cos theta equation, to each of the subset. Suppose for example, in water the bond angle is 105 degree. So here cos theta is equal to, please switch off your microphone. Mr. Pramod Kumar Das, please switch off your microphone. So here in water, the bond angle is 104 degrees 5 minutes. So the cos theta here, it is minus 0.250, and for the P is zero point 0.8, which indicates 80% character P character and 20% S character. So if we calculate the net P character over all the four orbitals in oxygen, then it must be 3, because it is Px plus Py plus Pz, and the total S character, it should be 1. So as the bonding orbital, it contains more p character, then the non-bonding character orbital, it will have less p characters. So we will understand that trigonal and tetrahedral hybridizations are probably restricted to molecules like BCl3 and CH4, which has identical substituents. When we have 5 coordination, most of the compounds of the nonmetals, they form the TBP structure, which has the symmetry, that is D3H. But the square planar structure is also found in such 5 coordination complexes, and here the dynamic equilibrium between TBP and square pyramidal structure has been shown here. Then coming to the Bend's rule and energetics of hybridization. So we know, we have already learned from LCAO that uh, where the resulting the resulting hybrids are having energy which is a total average of the atomic orbitals that take part in the bonding. So here, when we look into figure 2.17, when carbon forms four covalent bonds, there is a promotion of energy of 1s to 2s to 2p2 to 1s to 2s1 2p3. So here, this is the energy level of carbon, we know this is 2s2 and 2p2. Then the it upon gaining energy, it forms 2s1 and 2p3. So in the phosphorus atom, the there is a little initial promotion energy. The ground state is trivalent, so as is the valence state, the hybridization will cost energy. as a filled 3s orbital is raised in energy, and half 3p orbital they are lowered in energy. So one can find out the strength of the bonds by the magnitude of the bond energy from the total energy of hybridization. So in table 2.6 we can see the bond angles in the hydrides of groups of 15 and 16. So this is between NH3, PH3, ASH3 and SBH3. So we see the bond angles, and then we can it which considerably decreases. The bond angle it decreases as we move from the first element to that in the across the uh, here in this table you can see. So as the hybridization of the central phosphorus atom it requires more energy, the structure which utilizes the pure p orbitals in bonding it allows the lone pair to go inside a pure s orbital and is favored. But both the bonding and the non bonding electrons that are present they repel each other and they do not favor this, so a distorted tetrahedral structure results. So in the case of small sized elements like the N and O, the steric effects they come into play, but not in the larger atoms, such as those of phosphorus, arsenic, antimony, sulfur, selenium, and all such type of atoms. So for these larger atoms, the reduced hybridization energy of the more p character can be seen. This is for the sp3 hybridization in bonding orbitals. Here it is 3s2 and 3p3. Then with the change in energy this is how the sp3 hybridization in bonding orbitals it shows. So how the bond energy changes with hybridization is also a very important factor, and it will decide that which of the structure that results from this hybridization is more stable. The directed lobes of the sp hybrid overlap more effectively than the undirected orbitals. The two lobed p orbitals or the diffused d orbitals they give whichever gives the better overlap is preferred. So once the overlap is better, so whatever may be the nature of the overlap or the orbitals that are involved, then that structure is preferred. So in this table we can see the effect of the differences in hybrid bond strengths by the bond lengths in mxn molecules with the equatorial, that is the r equatorial and r axial substituents. Here it has been given. So a sp3 orbital, it is we know it is a combination of pz and dz square and spx py hybrids. So two linear hybrid orbitals they bond axially for and trigonal equatorial they bonds for the sp2 type. The sp2 hybrid orbitals they are shorter than the weaker axial bonds. It is always known that the sp2 hybrid orbitals they are shorter than the axial bonds. So when even experimentally it has been found that when substituents on the phosphorus atom they differ from the mixed like mixed chlorofluorides, that is PCl and F, then the alkyl phosphorus fluorides, that is RPF, the more electronegative substituent they occupy the axial position, and the less electronegative substituent they occupy the equatorial position. So this is an example of a Bend's rule. So when we generalize this Bend's rule we can say that when we have a more electronegative substituent they prefer hybrid orbitals which has less S character, and more electropositive substituents they prefer hybrid orbitals which has more S character. So although this is an empirical formula, molecular orbital calculations have also been found to satisfy that rule. A second example of Bend's rule is provided by fluoromethane, that is CH2F2. So here in CH2F2 the FCF bond is 109 degree and 5 minutes, so which indicates that it has less than 25% S character. But when we look the HCH bond angle, it is larger, and the CH bond it has more S character. So this is how is a typical example of a Bend's rule which correlates the bond length and the electronegativity. So similar observations have also been found for the bond angles of other fluoromethanes. Now this phenomena is often called as apicophilicity. So this apicophilicity explains which substituent they will occupy the orbital typical orbitals in the TBP structures. So this also even this apicophilicity has been explained in the case of oxysulfurants. So Bent's rule is also consistent with and provides very alternative rationalization of the Vesper model. When we apply the Bent's rule with the in combination that talks of the electronegativity and the nature of the S character or P character, so here the it is an exact prediction of the geometry of the molecule. So according to Bent's rule, that highly electronegative substituent, they will attract P character and reduce an electronegative substituent, and strong S-rich covalent bonds, they require a larger volume to bond. So what happens is doubly bonded oxygen, despite the high electronegativity, it always tries to find S-rich orbitals. Again, this explanation is also in accordance with the Bend's rule, which predicts the larger angular volume for the double bond of the oxygen atom. So now coming to geometrical and optical isomers. So, a classification on the isomerism, different types of isomerism in metal complexes, it has been shown in this figure. Isomerism has broadly been it has been classified into two types. One is the structural isomerism, another is the stereoisomerism. Structural isomerism has further been classified into ionization isomerism, hydration isomerism, ligand isomerism, linkage isomerism, isomerism, coordination position isomerism, and polymerization isomerism. But the stereoisomerism is classified further subdivided into two parts. One is geometrical isomerism and other is optical isomerism. So geometrical isomerism and optical isomerism, we will talk about this. So stereoisomerism, they, what do you mean by stereoisomers? The stereoisomers means they have similar metal ligand bonding sequence, but the arrangement of the atoms is different. So it has been divided into two classes. One is geometrical and the other is optical. So the geometrical isomerism, it occurs when the ligands can assume different positions with respect to the central metal atom. Like for example, the PTNH3 whole 2 Cl2. This is the cisplatin. It has been cis and transplatin. It has been shown here. It has this compound. It has two possible structures. So one is the cisplatin and another is the transplatin. So in the cis isomer, the two ammonia molecules here, they are cis to each other, whereas in the trans molecule, then the two ammonia molecules, they are trans to each other. So this type of isomerism is not possible for complexes where coordination number is 2, 3 or 4. That is particularly this geometrical isomerism or cis trans isomerism is not possible for molecules which has linear structure, trigonal planar structure or tetrahedral geometry. So this is only possible for molecules which has, when coordination number is 4, then only square planar complexes it is possible. Now when we have square planar complexes of the type MA4 or MA3B or MAB3, so geometrical isomerism is not possible. But if we have coordination number of the, but if we have with complexes like Ma2B2, Ma2BC, or total 4 different ligands, that is MABCD, or here if we have a bidentate ligand like MAA whole 2, so here we can see they give rise to geometrical isomers. Like for example, if we have the compound, the cisplatin that we talked of, Ma2P2, then there are two possibilities. One is cisplatin and other is transplatin. Then for the compound Ma2BC, so here like platinum, here we have biamino, bromo and chloro. So here it also gives rise to two types of isomers. But when we have total four different ligands that is attached to the central metal atom, then here these are the three types of arrangements that are possible. So this is the isomers possibles in square planar complexes. Now we will look into the bridged binuclear planar complexes like PtCl2, I2, PET3. Here it exists in three isomeric forms, as here it has been shown. The isomers, one, this is the trans isomer, this is the cis isomer, and this is the unsymmetrical isomers. So these three types of isomerism is possible for bridging binuclear square planar complexes. Then we will talk of six coordinated octahedral compounds. So we know octahedral compounds, they are six coordinated, so they may be of different types like Ma4B2, Ma3B3, Ma3B2C, Ma3BCD, Ma2B2CD, and Ma2BCD, or MABCDEF. That is totally six different ligands are attached to it. So now we will see octahedral, with when we have a octahedral geometry, a large number of isomers are possible. So whether they can be separated or not is a different question, but the possibility of a large number of isomers can be seen with octahedral geometry. So as we increase the number of ligands, the possible number of isomers also increases. So for example, we will see Ma2B2 type. So this type of octahedral complex will always give two ligands. Like here, one is for the cis isomer and the other is trans isomer. Then we will again consider a octahedral complex of the type Ma3B3. So here we also get two types of isomers. One is the facial isomer and the other is called as the meridional isomer. Here it has been shown in figure 2.23. So in the facial isomer, that is the one ligand, they lie in one side. Here you can see the Ma3B3, but on the meridional ligands, that is in the facial ligand, the three ligands of one type, they form one triangular face of the octahedron, and the other three are on the opposite side. Here you can see in the figure A, whereas in the meridional isomer, you can see one set of these ligands, they are arranged around an edge of the octahedron, whereas the other set, it occupies the other edge. That is, here one set of the ligands, that is here one AA, one set is arranged in this side, whereas the other, that is the AB, it goes to the other side. So when the ligands are arranged in one side of the octahedron, it is called as facial, and when it is opposite sides it is arranged, then it is called as meridional. So this is of the complex Ma3B3 type. So here, while writing an complex in figure 2.24, you can see the geometrical isomers of Ma2B2CD. So as the number of ligands increases, the possibility of the isomers also increases. So here in this case, six different isomers are possible when we take a octahedral complex of Ma2B2CD type. So while writing the geometrical isomers, we will always take into account the relative positions of the ligands must be different in each configuration, and it is not just a rotation. So we will always write down the different configuration of each of the ligand, not just by simply rotating the just shifting the position of the ligand, but we will always look what are the different possibilities. So the trick in writing these configurations is that we fix the position of some ligands initially and rotate the other ligands, and then for the isomer we write the configuration with the opposite ligands. So once, suppose for example, once we have fixed the cis position, we can write the all possible configuration of the cis position. Then we will write the opposite of the cis position, that is the transposition, and rotate the other ligands. But this requires lot of practice while predicting the possible isomers of an octahedral complex. So now coming to the optical isomerism. So, two isomers which have almost identical physical and chemical properties like melting point, boiling point, density, color, but they differ in the way they rotate the plane polarized light. We know they are called as the optical isomers, and this activity is called as optical activity. The such type of compounds which exist in pairs, and they are called as stereoisomers or enantiomers. These isomers, we know they are non-superimposable mirror images of each other. So any molecules which contains a center of symmetry or a plane of symmetry or a chiral symmetry, it will not show optical isomerism. So that is why optical isomerism is very rarely observed in square planar complexes. Now, when we have tetrahedral complexes of MAB2, there where we have AB is a bidentate ligand, then it can show our optical activity. So here this is optical isomers of MAB2. That means AB is a bidentate ligand. This is the metal. So this is one side, it is AB ligand is attached, and here this other side AB is attached. Then this is the mirror image. So we see that they are non superimposable mirror image, and hence it shows optical isomerism. However, optical isomerism is very common with octahedral complexes of these types. So here it has in few examples of the optical isomers of cobalt ethylene diamine, triethylene diamine, it has been shown here in this figure. How we can say this is for octahedral activity, this octahedral complex. So with this, the part on isomerism is over. So in summary, we can talk of that we studied the different types of isomerisms, particularly geometrical and optical isomerism, the Bend's rule, the Vesper theory of predicting molecules, the geometry of the molecules. So with this, we finish this part. We'll just take a break of 5 minutes and again resume with the new chapter. So here in this unit, we'll start with organometallic chemistry. So first is the organometallic compounds. So in this unit, we will talk of the classification and nomenclature of organometallic compounds, the different types of organometallic compounds of the group 1 and group 2 elements, their synthesis, structure, bonding, properties, and also we'll talk about the transition metal alkyl and aryls, the methods of synthesis and their decomposition pathways. Also, we'll have a special focus on organocopper compounds and its applications. So first is we'll start with the classification and nomenclature of organometallic compounds. So organometallic compounds was the first organometallic compound that was discovered was the Zeiss salt, and with the discovery of this Zeiss salt, then the a new chapter in inorganic chemistry it opened, and it was the organometallic chemistry. So here first we will learn about the definition and classification of the different types of organometallic compounds. So how do we define a organometallic compounds? So these compounds, particularly in a simple definition, they are defined as those compounds which contain at least one metal to carbon bond. So where the metal may be non-metals like boron, silicon, phosphorus or arsenic, and the ligands, they are organic compounds, and but also they can be like CO, which is carbonyl, cyanide, acetate, and such type of ligands. So basically when we have a metal to carbon bond, then we call it as the organometallic compound. So when we have compounds like titanium OET4, calcium NMe2, these are not organometallic compounds. Whereas, but when we have phenyl titanium OET3, these are organometallic compounds. So carbides, cyanides, and carbonates, they are not included in as ligands. Metal carbonyls, they are a special class of organometallic chemistry, and they involve the transition metal chemistry. So organometallic generally it denotes a compound in which organic groups are directly linked to the metal at least through one carbon bond. That is, there should be at least one metal to carbon bond in the complexes. Now, the nature of this metal to carbon bond, it determines the type of the organometallic complex. So first we will learn the classification of organometallic compounds depending on the nature of their metal to carbon bond. So first, organometallic compounds whereas there is metal to carbon sigma bond, that is the metal belongs to the main group chemistry. So this is the first class where the metal are main group elements and the bond is sigma bond. Secondly, the organometallic compounds may be formed by sigma donor and pi acceptor like carbon monoxide, or we call this the carbonyl ligands. Thirdly, the organometallics, they may be formed by pi electron donors, for example, like the olefins and other pi systems. And lastly, organometallic compounds can also be formed of highly electropositive metals, and they are mostly ionic nature, and they totally form a different class of organometallic chemistry. So here we should always remember that transition metal organic compounds, they are immensely, they have varied and in their structure and bonding types. Why transition metal are mostly present in organometallic chemistry? It is because the transition metals, they can use their s and p orbitals, and particularly the d orbitals, in bonding. So each orbital type, they can either donate or accept the electron density. So just in the bonding of coordination compounds, the d orbitals on the metal, it matches with the orbitals in the organometallics to interact with the s and p orbitals. So unlike conventional transition metal complexes, the central metal atom that is in an organometallic compound is present in a very low oxidation state. Now, because of this flexibility, the transition metal organic compounds, they play a crucial role in the chemical industry. So here a portion of that periodic table is given, and the different types of bonding that are possible with electropositive elements and the d block elements, it has been shown. So here with the group 1 elements, you see the bonding is mostly ionic nature. Here group 2 and group 13, here it is covalent structure. The d block transition elements, they form both anionic sigma donors ligands and with anionic and neutral pi donor ligands. Even electron deficient structures have been known from the d block elements. The main group elements, they form volatile compounds with anionic sigma donor groups. So this is how uh, a classification, the different types of bonding in organometallics have been done. So first is the ionic organometallic compounds. The lanthanoids, actinoids and the metals of group 1 and 2 which have electronegativity less than 1, we know that they are very high electropositive elements. So their organometallic compounds are predominantly ionic in nature. But we know that those of lithium, beryllium, and magnesium, they have highly better covalent character. So their stability and reactivity, it is determined by the stability of the carbanion. The compounds which contain CnH2n plus 1 minus an ion, they are not stable and difficult to isolate. So if the electron density of the carbanion is delocalized, then stable salt-like compounds are obtained. Such compounds are also highly reactive. Like for example, C5H5Na and C5H5 2Ca. So where the negative charge is delocalized over the pi electron density. So examples of simple organic compounds are methyl lithium for group 1, dimethyl beryllium for group 2 and trimethyl boron for group 13. So these are simple organometallic compounds. Then covalent sigma bonded organometallic compounds. The sigma bonded organometallics, they are formed by most of the nonmetals and also by metals of low positive character. The transition metals, they form fewer sigma bonded compounds and those are highly reactive. The MC bond in such type of compounds, they are called as 2C2E bond. That means they are two centered, two electron bond and a partial substitution of halogen or similar groups occur, like in case of Me3 SnCl, Me SnCl3, etc. But when we have MC bond in these compounds, they also have a certain ionic character. So unlike the main group elements, transition elements, they form fewer simple alkyls or aryls. Now these compounds, they are unstable under ordinary conditions. We have stable alkyl and aryl compounds with are known such as with other pi acceptor ligands. So, stable cobalt to carbon bond is present in nature in vitamin B12 related compounds, often due to coordinately unsaturated metal centers. The MC sigma bonds, they are very weak and compound these such type of compounds which contain metal carbon sigma bond, they decompose easily, resulting in high reactivity. Then coming to non-classical multi-center bonding and pi complexes. So the nature of bonding in such type of organometallic complexes, that is in pi multi-center complexes, they cannot be explained by the 2C2E bond. That is the alkyls of lithium, beryllium and aluminum. They have been known to show multi-center bonding type. So further examples of this such type of complexes can be found in transition metal, like the common example here is xysalt or ferrocene. The non-classically bonded compounds may be divided into two classes. So first is the organometallic compounds that have bridging alkyls like dimeric trialkyl aluminum, that is Al2R3, or a polymeric dimethyl beryllium, that is BeMe2 whole to the power n. Even we can say diethyl magnesium. These are all the polymeric structure. So the structure of dimethyl beryllium, here it has been shown, and the structure of dimeric trialkyl aluminum, it has been shown here. So such type of complexes, they join together by bridges. They are called as the alkyl bridges. The metal that is present, the two metals, they all the ligands, they are equidistant from the two metal atoms. So here the nature of bonding cannot be explained on the basis of 2C2E bonds, as the bridging carbon cannot be simultaneously bonded to two metal atoms and three substituents. So, in the case of dimeric compounds of aluminium trialkyls, two types of aluminium to carbon bonds have been noted. One is the terminal aluminium to carbon bond, which is 2C2E in nature, while the bridging are 3C2E electrons in nature. So that is why when we have dimeric compounds, then two types of metal to carbon bonds are noted. That is the terminal, and other is the bridging. Then coming to pi bonded organometallics. So these are transition metal complexes with unsaturated organic compounds where there is interaction between pi orbital of the organic ligands and the d and p orbitals of the metal atom. So compounds with alkenes, alkynes and cyclic compounds having delocalized pi electron orbital, they fall under this category. The examples of such ligands are like alkene, butadiene, allyl, cyclopentadiene, benzene, etc. We have the most important pi bonded organometallic compound is ferrocene, that is FeC5H5 whole 2, even dibenzyl chromium, and the first organometallic compound that was discovered, that is Zeiss salt. So some common ligands that have been used in organometallic chemistry, first is the CO, that is the carbonyl CH3 is methyl, this is the N-butyl, the tertiary butyl, the C5H5 minus is the cyclopentadienyl ion and it is represented as small p. C6H5, that is the phenyl, C6H6 is the benzene, then we have the C6H5 whole 3 phe, P, that is triphenyl phosphine, then hydride, fluoride, chloride, bromide, iodide, the cyanide, the bridging fluoride, the bridging carbonyl, and the nitrosyl, the trialkyl phosphine, then trihalide phosphine, all such type of, these are the common ligands that we come across in organometallic chemistry. Then coming to the concept of hapticity. So what is this hapticity? This the is based on the bonding potential of an organic compound and it is represented as eta raised to the power x. So if eta is equal to 1, then it is monohapto. If it is eta is equal to 2, that is it is dihapto. So accordingly we can indicate or we can know the hapticity. So hapticity is defined as the number of carbon atoms within a bonding distance of the metal atom or the number of carbon atoms through which an organic ligand is attached to the central metal atom. That is, in simple terms, we can define as the hapticity as the number of carbon atoms through which the ligand is attached to the central metal atom. So here if we look into this figure 4.5 hapticity, in the first case it is cyclopentadienyl and this is hapticity is eta raised to the power 5. So in the second case it is the hapticity is 3 and that is eta raised to the power 3. For the allyl here it is eta raised to the power 3. It is allyl, and for the eta raised to the power 1 this is for your allyl ligand. So coming to classification of organometallic ligands and their hapticities. So when we have monohapto, then so the example is carbine or carbide, then we have carbene, alkyl, alkyl, aryl. So the complexes with the examples have been shown here. Then for dihapto, it is alkene, alkyne, and then this is the certain bridging complexes. The examples have also been shown here. Then for trihapto, we can see this is the allyl group, N-allyl group. For tetrahapto, it is mostly cyclobutadiene or the conjugated diene. Then for pentahapto, it is cyclopentadiene or the cyclopentadienyl derivatives. Here example has been shown. Hexahapto, we have the arene complex here, and heptahapto is a very common ion that is called as the tropylium ion, or we call it as the cycloheptatrienyl. And for the octahapto, that is cyclooctatetraene, that is eta raised to the power 8. So these are some of the common ligands and their hapticity has been given here. Then coming to organometallic compounds of certain group 1 and group 2 metals. So here first we will start with methyl lithium. So methyl lithium is CH3 Li. So methyl lithium, it exists. The tetrameric and the hexameric forms of methyl lithium has also been identified using spectroscopy. The tetrameric form has been shown here in this methyl lithium. You can see this is the tetrameric methyl lithium. So here the four lithium lithiums, they occupy the alternate diagonal corners of the tetrahedron. The carbon of the methyl group, they occupy the four vacant corners of the cube, which are also the, that is the alternate diagonal positions. So each methyl carbon atom, it is above the face of a hydro of the tetrahedron, and it forms a bridge with the lithium atom over the face of the tetrahedron. So this structure is that of a distorted cube. The intramolecular lithium to carbon distance is 231 picometer, and here the carbon is not only bonded to three H atoms, but it is also bonded to a lithium atom here, as it has been shown here. If we look here, then the carbon is also bonded to a lithium atom. So thus the coordination number for the carbon atom here is 7. So in a similar way, the coordination number of lithium is also 7. So here we will always remember that for tetramethyl lithium, the coordination number is 7, and for carbon it is also 7, and for lithium it is also 7. Then we have another class of compounds, those are the beryllium sandwich compounds. So here it is done when we beryllium alkyl compounds, they are prepared by heating mercury dialkyl with the metal. So the alkyls of beryllium, they are mostly liquids, very reactive liquids or solid. So here BeMe2, it is linear, but the solid state a polymeric structure here it has been shown, and BeCl2 is represents two types of bonding. One is the 3 carbon 2 type bonding. Here it has been shown in such type of BeMe2 polymeric compounds. However, here the aryls are prepared with the help of the reaction between the lithium aryl and BeCl2. That is phenyl lithium plus BeCl2, it forms the diphenyl beryllium compound. Cyclopentadienyls of that is the BeCp2, that is dicyclopentadienyl barium, can be shown prepared by this way. And this, the X-ray diffraction and the structure here it has been shown like this for BeCp2. Since these rings, they are very weakly bonded, and then we can say that such type of compounds, they are called as the atomic beryllium. It is sandwiched between the two cyclopentadienyl group, and that is why such type of compounds, they are called as your sandwich compounds, particularly beryllium sandwich compounds, and these are very common in beryllium chemistry. So with this, we talked about the beryllium sandwich compounds. The in the next part we'll continue with this further with the organometallic compounds. So this much for today.
ହ୍ୟାଲୋ ହ୍ୟାଲୋ ଅଭିଜିତ।
ହ୍ୟାଲୋ।
ହଁ ତମର ବାୟୋଲୋଜି ନା କଣ?
ହଁ ହଁ। ଭାଇ
ଏଇ କେତେଟା କଣ ଆସାଇନମେଣ୍ଟ ଲେଖିବାର ଅଛି?
ଏଇତ ଚାରିଟା ତ ଦେଇଛନ୍ତି ଆଉ ତ କୋଶ୍ଚିନ୍ କଣ ଆସିନି ନା କଣ?
ନାଇଁ ମାନେ କିଏ କହୁଛି କଣ କିଛି ଜାଣି ହଉନି ଜମା। ମାନେ ଦେଖ ଗୋଟେ ହେଲା ଜେନେରାଲ ଫିଜିକାଲ କେମିଷ୍ଟ୍ରି।
ହଁ ଆମର 11, 12, 13 ଆଉ 14ଟା ଅଛି ମ୍ୟାଥମେଟିକ୍ସ ସେଟା ତ ଆମର ନାହିଁ। ଆମର କଣ ହଉଛି
15।
15ଟା ହଉଛି ଆମର ବାୟୋଲୋଜି ସେଟା ଲେଖାଯିବ।
ଆଚ୍ଛା
ତାପରେ
ମୋର ଗୋଟେ କୋଶ୍ଚିନ୍ ଥିଲା ଯେ 11ଟା ଯୋଉଟା ସେଇଟା ତ
ଆଜ୍ଞା
ଅନଲାଇନରେ ମାନେ ସାଇଟରେ ଇଗ୍ନୋ ସାଇଟରେ ଦେଖିଲେ ସେଇଟା ତ ତାର ଲାଷ୍ଟ ଥିଲା ଜୁନ 2025। ସେଇଟା କଣ ଆମେ ଲେଖିବା ପୁଣି?
ନା ଆମର ପା ଅଛି ଡିସେମ୍ବର 2025 ପର୍ଯ୍ୟନ୍ତ ସେଇଟା ଅଛି ପୁରା ଦେଖିବେ ତ ସାଇଟରେ ଅଛି। ଗୋଟେ ଅଛି
ନାଇଁ
24
ନାଇଁ
ମସିହାରେ ଅଛି ଆଉ
ଡିସେମ୍ବର ପର୍ଯ୍ୟନ୍ତ ଅଛି ଯେ କିନ୍ତୁ ଯୋଉ MCH-011 ଯୋଉ କୋଶ୍ଚିନ୍ PDF ଟା ମାରିଲେ ସେଇ କୋଶ୍ଚିନ୍ PDF ରେ ସେଇଟା ତାର ଲାଷ୍ଟ ସବମିଶନ ଜୁନ 2025 ଲେଖାହେଇଛି।
ସେଟା ଫାଷ୍ଟ ସେମିଷ୍ଟାର ପାଇଁ ଆମେ ଯେହେତୁ ଇୟରଲି ବେଷ୍ଟ ଦଉଛୁ ନା ସେଇଥିପାଇଁ ସେଟା ଲେଖୁଛି ମାନେ ସେଟା ଫାଷ୍ଟ
ଆଚ୍ଛା
ସେମିଷ୍ଟାର ଦେଇଥାନ୍ତେ। ଫାଷ୍ଟ
ଆଚ୍ଛା ଆଚ୍ଛା
ସେମିଷ୍ଟାର ଜୁନ ମାସ ଗୋଟେ ହେଇଥାନ୍ତା ତ ସେଇଥିପାଇଁ।
ଆଚ୍ଛା ଆଚ୍ଛା ହେଲେ ଆମର
ଆମେ
11, 12, 13, 15।
15 ହଁ।
ଆଉ କିଛି ନାହିଁ।
ଆଉ ଆପଣଙ୍କର ଆସିଛି ନା ବହି ଆସିଛି ନା ପଛରେ ଆଉ ଆସିନି?
ମତେ ତ ପରେ କେତେଟା ପ୍ରାକ୍ଟିକାଲ ଆଉ ଗୋଟେ ଦିଟା କଣ ଗୋଟେ ଆସୁଥିଲା।
ନା ମୋର
ଫାଷ୍ଟ
16
ଗୋଟେ ବାର
ନମ୍ବର
ତେରଟା
17
ପଳେଇ
ନମ୍ବର
ଆସିଥିଲା।
ଆସିଛି 16, 17 ଆସିଛି।
ହଁ।
ଆଉ ଆଜି କାହିଁକି ଭାଇ ୟୁନିଟ 3 ଟା କାହିଁ ପଢେଇଲେନି?
ୟୁନିଟ 3 ଟା କଣ ପଢା ହେଲା ବା ନା ପଢା ହେଲାନି?
ନା ପଢା ହେଇନି ଡାଇରେକ୍ଟ ତ ୟୁନିଟ୍ 4।
ଆଚ୍ଛା। ଓହୋ ମତେ ଲାଗିଲା କି ୟୁନିଟ 2 ପରେ ୟୁନିଟ 3 ପଢେଇବେ ମୁଁ ଇଆଡେ କ୍ଲାସ କରୁଛି ପ୍ଲସ ଇଆଡେ ଆସାଇନମେଣ୍ଟ ବି ଲେଖୁଛି।
ଓହୋ କେତେଟା ସାରିଲେଣି ଆପଣ?
ମୁଁ ଏବେ 12 ଆଉ 15ଟା ସାରିଦେଲିଣି ଏବେ 13ଟା ଚଲେଇଛି।
ଓହୋ ନା ମୋର 13 ଚାଲିଛି ଆଉ କିଛି ଆଗେଇନି ଦେଖାଯାଉ ଏଇ 15-16
ନା
ଦିନ ଭିତରେ ସରିବ ଆଉ।
ସବୁ ଆଡକୁ ଦେଖିବାର ଅଛି ନା ସେଇଥିଲାଗି ମାନେ ଗହଳି ପୁରା ମାନେ ମୁଣ୍ଡ କିଛି କାମ କରୁନି କିଏ କହୁଛି 8ଟା ଏ ଯୋଉ ଆଜିକାଲି କେତେଟା ଅନଲାଇନରେ କହୁନାହାନ୍ତି କି ଆମେ ଆପଣଙ୍କୁ
ହଁ ହଁ
ସବୁ
ହଁ।
ଆସାଇନମେଣ୍ଟ ଦେଇଦବୁ ଇଏ କରିଦବୁ ସେ କରିଦବୁ। ଦେଖିଲା ବେଳକୁ ସେ କହୁଛନ୍ତି 3,000 ଟଙ୍କା ଦିଅ 8ଟା ଯାକ ଦିଆହବ।
ନାଇଁ ନାଇଁ ଏଟା ଖାଲି କିଛି ଦରକାର ନାହିଁ ଏଟା ହଉଛି ଆମର ଆମେ ଗୋଟେ ବର୍ଷରେ ଯେହେତୁ ଦବା ତ ସେଇଥିପାଇଁ
ହଁ ମଝିରେ ସେ କିଏ
ଫାଷ୍ଟ ସେମିଷ୍ଟାର
ଏଜୁକେସନ
4ଟା
କିଏ
ସେକେଣ୍ଡ
ଅଛି
ସେମିଷ୍ଟାର 4ଟା।
ନାଇଁ ନାଇଁ ଗ୍ରୁପ ରେ କିଏ ଗୋଟେ ଏଜୁକେସନ ଅଛି ରାଜାରାମ ଦାସ ବୋଲି ତା ସହିତ
ଆଜ୍ଞା
ମୋର କଥାବାର୍ତ୍ତା ହେଇଥିଲା। ହେଲେ ସିଏ କହୁଥିଲା କି କଣ ମୁଁ ପରେ ପଠେଇବି ବୋଲି ଆସାଇନମେଣ୍ଟ ଗୁଡାକ ମଝିରେ ଗୋଟେ ଥର ପଠେଇଥିଲା ନା ସଲଭଡ ଆସାଇନମେଣ୍ଟ ବୋଲି।
ନା କି କୋଉ ଜଣେ
ସେଇଟା
ଭଉଣୀ ପରେ ଜଣେ ପଠେଇଥିଲେ ପୁରା ଯୋଉ ଆମର 15 ପର୍ଯ୍ୟନ୍ତ ପଠେଇ ଦେଇଥିଲେ।
ହଁ ପଠେଇଥିଲେ ପୁଣି ସେଟାକୁ ଡିଲିଟ କରିଦେଲେ ଏଭ୍ରିୱାନ ଡିଲିଟ କରିଦେଲେ। ବାକି ମୁଁ ତ
ଓହୋ
ନେଟ ରୁ ଲେଖୁଛି।
ଓହୋ ନା କିଛି ଅସୁବିଧା ନାହିଁ ସିଏ
ହଁ ହଁ
ଦେଖାଯାଉ
ହଁ
ନା
ହଉ ଆଉ
ଜଣେ ଯୋଉ ପଠେଇଥିଲେ ସେ ଡିଲିଟ କରିଦେଲେ ନା କଣ?
ହଁ ବା। ଯୋଉ 3-4ଟା ସଲଭଡ ଆସାଇନମେଣ୍ଟ ପଠେଇଥିଲେ କିଏ ଗୋଟେ ଜଣେ
ହଁ
ସିଏ
ହଁ
ପୁଣି
ହଁ।
ଆଉଥରେ ଡିଲିଟ ଫର ଏଭ୍ରିୱାନ ହେଇଗଲା ମାନେ କରିଦେଲେ।
ଓହୋ।
ସେଇଟା ନହେଲେ ମୁଁ ତ ଏମିତିରେ ନେଟ ରୁ ଲେଖୁଛି ବାକି ସେଇଥିରେ ଆହୁରି କେତେଟା ଥିଲା। ଏମିତି ଆଉ
ରହିଥାନ୍ତୁ ମୋ ପାଖରେ ଯଦି ଥିବ ତ ମୁଁ ପଠେଇଦେବି ରହିଥାନ୍ତ ମୁଁ ତ ଡାଉନଲୋଡ ମାରି ରଖିଥିଲି ନା କଣ। ଦେଖତେ
ଆଚ୍ଛା
ପଡିବ ବୋଧେ।
ହଁ କିଛି ଅସୁବିଧା ନାହିଁ ବାକି ମୋର ଖାଲି ଗୋଟେ ଜିନିଷ ଜାଣିବାର ଥିଲା। ସେ ଯୋଉ 12 ନମ୍ବର ଯୋଉଟା ଷ୍ଟେରିଓ କେମିଷ୍ଟ୍ରି ତାର
ଆଜ୍ଞା
ଲାଷ୍ଟ ଯୋଉ କୋଶ୍ଚିନ୍ 10 ନମ୍ବର ର ଲାଷ୍ଟ 3 ନମ୍ବର ଇକ୍ୱେସନ ଟା ମାନେ କଣ ହବ ପ୍ରଡକ୍ଟ ଟା ଖାଲି ସେଇଟା ନହେଲେ ବାକି ମୁଁ ତାର ମେକାନିଜିମ ବି ଲେଖିନି।
ଅଛି ଅଛି ଭାଇ ଅଛି ମୁଁ ପଠେଇଦେମି ହେଲା ଆମର ଅଛି ସେଇ ପିଡିଏଫ୍ ଗୁଡା ସବୁ ଅଛି। ମୁଁ ତାର ଯାଉ ଡାଉନଲୋଡ
ହଁ
ମାରି ଦେଇଥିଲି।
ନାଇଁ ହ୍ୱାଟ୍ସଆପ ରେ ତମ ନାଁ ଅଭିଜିତ ଲେଖା ହେଇଛି ତ?
ଆଜ୍ଞା ଆଜ୍ଞା ଅଭିଜିତ ପାଣିଗ୍ରାହୀ।
ହଁ ହଁ ଘର କୋଉଠି କି?
ଘର ଖନ୍ତାପଡା ବାଲେଶ୍ଵର।
ଓ ବାଲେଶ୍ଵର ପଟେ ନା।
ଆଜ୍ଞା ଆପଣଙ୍କର?
ମୋର ମାଲକାନଗିରି।
ଆଜ୍ଞା ଶୁଣା ଗଲାନି।
ମାଲକାନଗିରି।
ମାଲକାନଗିରି ଆଜ୍ଞା।
ହଁ
ହଁ ଆପଣ ଟିକେ
ଭାଇ
ହାଇ
ମତେ
ପଠେଇ ଦିଅନ୍ତୁ, ମୁଁ
ଛାଡିଛି ଏବେ।
ପଠେଇଦେବି ଆଜ୍ଞା।
ହଁ
ହଁ ଏଇ ଯୋଉ
ହଉ
ଲାଷ୍ଟ କୁ
ଠିକ ଅଛି।
77 ଅଛି ତ?
ହଁ
ହଉ
8658673677।
ଆଜ୍ଞା ହଁ ଆସିଛି ମୁଁ
ହଁ
ପଠେଇଦେମି ଭାଇ, ଅଛି ସବୁ ଗୁଡାକ ଅଛି ଆସାଇନମେଣ୍ଟ ଗୁଡାକ। 15
ହଁ ହଁ
ପର୍ଯ୍ୟନ୍ତ ଅଛି, 15 ପର୍ଯ୍ୟନ୍ତ ଅଛି, ମୁଁ
ହଉ
ପଠେଇଦେମି ଆଜ୍ଞା।
ହଁ ମୁଁ ତ 15 12 ଲେଖିଦେଇଛି ଆଉ 13 ଆଉ 11ଟା ବାକି ଆଉ।
ଆଜ୍ଞା ଆଉ ବି ଯିଏ ମାଗିବେ ଯଦି ତାଙ୍କୁ ସାହାଯ୍ୟ କରିଦେବେ ହେଲା, କାହିଁକି ନା ସମସ୍ତେ ଆମେ
ହଁ
ବି
ହଁ
ହଇରାଣ ହଉଛୁ ଆଜ୍ଞା।
ହଁ ହଉ
ଆଉ
ଆଉ
ଦେଖାଯାଉ କଣ
ଆସାଇନମେଣ୍ଟ
ହଉଛି
ଟା
କାହିଁକିନା
କଣ ଯାଇକି ସବମିଟ କରିବ ନା
ହଁ ମୁଁ
ପୋଷ୍ଟାଲ ରେ ପଠେଇଦବ?
ଯାଇକି ସବମିଟ କରିତେ ପଡିବ, କାହିଁକିନା ସେମାନେ ହଉଛି ଆମର ବାଇ ପୋଷ୍ଟ ନେବେନି ପ୍ରାୟ, ତାପରେ ପହଞ୍ଚିବ କି ନ ପହଞ୍ଚିବ ସେଠି ଗୋଟେ ରିସିପ୍ଟ ଦେବେ ନା କଣ, ମୁଁ ତ ଜଣକୁ ବୁଝୁଥିଲି ସେ
ନାଇଁ
କହିଲେ
ମୁଁ ସେ
ଯାଇକି
ଯୋଉ ଏଜୁକେସନ ବୋଲି ତା ସାଙ୍ଗେ କଥାବାର୍ତ୍ତା ହଉଥିଲି, ଯଦି
ଆଜ୍ଞା
ସମସ୍ତେ ରାଜି ହେବେ ତାହେଲେ ଯାଇକିନା ସବମିଟ କରିଦବା କଥା, କାହିଁକି ନା ଗଲେ ବି ସମସ୍ତଙ୍କର ଗୋଟେ ମାନେ ଗେଟ ଟୁଗେଦର ବି ହେଇଯିବ, ସମସ୍ତଙ୍କୁ ଜାଣିଦବା।
ହଁ ଟିକେ ଚିହ୍ନା ପରିଚିତ ହେଇଯିବ ଜିନିଷଟା ଏକ୍ସାମ
ଚିହ୍ନା
ବେଳେ ଟିକେ
ପରିଚୟ
ସୁବିଧା
ସେଇଆ ଆଉ।
ହବ। ଆଜ୍ଞା
ହୁଁ
ସେଇ ଏଜୁକେସନ ତାଙ୍କ ଘର କୋଉଠି?
ସିଏ ଭୁବନେଶ୍ଵର କହୁଥିଲେ ବା।
ଓହୋ ସେଦିନ ଯୋଉ ସୁଜିତ ବୋଲି ନା କଣ, ସୁଜିତ ଭାଇ ନା କଣ?
ମୁଁ କହିପାରିବିନି କିଏ, ବାକି ସିଏ କହୁଥିଲେ, ଯିଏ କହୁଥିଲେ ଯୋଉ ମଝିରେ 90% ଯୋଉ ପିଲା ଫେଲ ହେଇଯାଇଛନ୍ତି, ଯିଏ କହୁଥିଲେ।
ଓହୋ ମୁଁ ଆଉ ଏତେ ତାହେଲେ ଖେୟାଲ ରଖିନି।
ସେଇଆ ବା
ହଉ
ଖାଲି
ଦେଖି
ଇଏରେ ତମ ନା ଯେମିତି ଅଭିଜିତ ଲେଖା ଅଛି, ତାଙ୍କ ନାଁ ରାଜା, ମାନେ ଟ୍ରୁ କଲର ରେ ମାନେ ହ୍ୱାଟସଆପ ରେ ତ ଏଜୁକେସନ ଲେଖା ହେଇଛି, ବାକି ଟ୍ରୁ କଲର ରେ ରାଜାରାମ ଦାସ ନା କଣ ଏମିତି ଆସୁଛି।
ହଁ ସେଇ ଯୋଉ ଯିଏ ଗ୍ରୁପ କ୍ରିଏଟର ଥିଲେ, ହଁ ତାଙ୍କରି ଠିକ ମନେ
ହଁ
ଆଉ ଦେଖାଯାଉ କଣ ହଉଛି ଠାକୁରଙ୍କ ଦୟାରୁ, କାହିଁକିନା ଇଏ ତ ଯେମିତି ପଢଉଛନ୍ତି ଆଙ୍କ ପଢା ମାନେ ବୁଝି
ହଁ
ହଉଛି
ବା
ଯେ, କିନ୍ତୁ ଅସୁବିଧା ନାହିଁ, କିନ୍ତୁ
ଆମେ
କେତେବେଳେ
ବିଇଡି ଯାକ କରିଦେଇଛୁ ଯେ ସେଗୁଡାକରେ କଣ ଖାଲି ଆମେ ଖାତା ଫୁଲ କରି ଲେଖିଦେଉଥିଲେ, କିନ୍ତୁ ଏବେ ତ ଏଇଠି ଯାହାହେଲେ ପାଠ ସବୁ ଲେଖିବାକୁ ପଡିବ।
ହଁ କାହିଁକିନା ଇଏ ଥରୁଲି ପାଠ ନା
ଦେଖାଯାଉ କଣ
ଜିନିଷଟା।
ହଉଛି।
ଗ୍ରାଜୁଏସନ ପାଠ ବି ୟା ଭିତରେ ଅଛି, ଆଜି ଯୋଉଟା ପଢଉଥିଲେ ସେଗୁଟା ସବୁ ଥିଲା।
ହୁଁ
ଆଉ ସି ଷ୍ଟ୍ରେସ୍
ତମର ଏଇନା
ମୋର
କଣ ଚାଲିଛି
ଅଛି
କି?
ଆଜ୍ଞା।
ପିଜି ସହିତ କଣ ଚାଲିଛି ଏକ୍ସଟ୍ରା ଆଉ?
ମୁଁ ଏଇ କମ୍ପିଟେଟିଭ ପାଇଁ ନଉଛି କୋଚିଂ।
ହଁ ସେଇ
ଆଉ
ତ
ଦେଖା
ସବୁ ଆଉ।
ଆଜ୍ଞା ଦେଖାଯାଉ କଣ ହଉଛି, କାହିଁକିନା ନିଜେ ଯଦି ନ ପଢିବା ହବନି କିଛି। ଆଉ ଟାଇମ ବି
ହୁଁ
ନାହିଁ
ହୁଁ
କରିହବ, ଏତେ ଗୁଡା 8ଟା ପେପର ହେଲାଣି। ଆଉ
ହଁ
ଗୋଟେ ବୁଝିଥିବି ପ୍ରାକ୍ଟିକାଲ ଟା କୋଉଠି ଦବା, ଆମର ଏଠି ଦବା ନା କଲେଜରେ ଯାଇକି ଦେବି?
ସେଇଟା ବି ମତେ ଜଣା ନାହିଁ, ବାକି ମୁଁ ବି ପଚାରୁଥିଲି। କିଏ କହୁଛନ୍ତି ଭୁବନେଶ୍ୱର ରିଜନାଲ ସେଣ୍ଟରରେ ଯିବା, କିଏ
କାହିଁକିନା
କହୁଛନ୍ତି
ମୋ
ଷ୍ଟଡି
ମୋ
ସେଣ୍ଟର ଯିବା।
ସାଙ୍ଗ ମୋ ସାଙ୍ଗ ଜଣେ ଫିଜିକ୍ସ ଅନର୍ସରେ ସିଏ କରୁଥିଲେ ଯେ, ସିଏ ତାଙ୍କୁ ପଚାରୁଥିଲେ ସେ କହିଲେ ଯେ 15 ଦିନ ଗୋଟେ ପ୍ରାକ୍ଟିକାଲ ହୁଏ ଫାଷ୍ଟ ଇୟରରେ, ସେଟା ଯାଇକି କଲେଜରେ ରହିକି ଦବାକୁ ପଡେ।
କଲେଜରେ
ଆଉ
ରହିବାକୁ ମାନେ କଣ, କଲେଜ ଭିତରେ ଆମକୁ ରହିବା ପାଇଁ ସୁଯୋଗ ଦେବେ ନା ଆମେ ବାହାରେ ରହିବା କୋଉଠି?
ନା ମାନେ କଲେଜରେ ହିଁ 15 ଦିନ ଲଗାତାର କ୍ଲାସ ହବ, ପ୍ରାକ୍ଟିକାଲ ହବ, ଆଉ ଆପଣ ସେଇଠି ପାଖାପାଖି
ନାଇଁ
କେଣ ମେସ୍
ରହିବାଟା
ରହିବେ, ନା ରହିବାଟା ନିଜ ହାତରୁ, ରହିବାଟା ମେସ୍ ଏକା ନେଇକି ରହିବେ ଆଉ।
ଆଚ୍ଛା
ଆଉ ସିଏ
ହଉ, ତାପରେ
ଏମପିସି
ଆଉ ଗୋଟେ
ଏମପିସି
କଥା ହେଲା, ଗ୍ରୁପ ତ କ୍ରିଏଟ ହେଇଛି, ଆମେ
ଆଜ୍ଞା
ସେ ଗ୍ରୁପ ରେ ଦେଖିଦବା ଯେ ବାୟୋଲୋଜି ଷ୍ଟୁଡେଣ୍ଟ ଆମେ କିଏ ସବୁ।
ହଁ।
ହଁ ତ ସେଇ
ତାପରେ
ହିସାବରେ ଗୋଟେ ଆଉ
ସମସ୍ତେ ବି ଟିକେ କୋଅର୍ଡିନେଟ କରୁନାହାନ୍ତି, ସମସ୍ତେ ଅଧେ ବି ସାଇଲେଣ୍ଟ ହେଇକି ରହିଯାଉଛନ୍ତି, ଜଣା ପଡୁନି। କିଏ
ହଁ
କୋଉଠି
ନାଇଁ
ଯାଇଥିବ କିଛି
ତାପରେ ଲାଙ୍ଗୁଏଜ ମାନେ ଟିକେ କମ୍ୟୁନିକେସନ ଟିକେ ପ୍ରୋବ୍ଲେମ ହଉଛି। କିଏ ଜଣେ
ଆଜ୍ଞା
କହୁଥିଲା ନା ଓଡିଆରେ କୁହନି ହିନ୍ଦୀ ଇଂଲିଶ ରେ କୁହ ବୋଲି।
ହଁ ସେଇ ଜଣେ
ମୁଁ
ଆମର
ସେଦିନ ପାଟି କରିକି କହିଲି ଯେ ଭାଇ ସବୁ ତ ଓଡିଶାରୁ, ଆଉ କାହିଁକି ହିନ୍ଦୀ ଇଂଲିଶ କହୁଛ, ଓଡିଆରେ କଥା
ହଁ
ହୁଅ। ପୁଣି କିଏ ଜଣେ ଗ୍ରୁପ ରେ ଚିଲେଇଲା, ନାଇଁ ଭାଇ ଟିକେ ହିନ୍ଦୀ ଇଂଲିଶ ରେ କମ୍ୟୁନିକେଟ କର। ହଉ ଠିକ ଅଛି।
ହଁ।
ସେଇଟା କିଛି ପ୍ରୋବ୍ଲେମ ନାହିଁ, ବାକି କଥାଟା ହଉଛି କି ଯାଇକିନା ସବମିଟ କରିବା ନା ପୋଷ୍ଟାଲରେ ଦେଇଦବା। ସେଇଟା ଯଦି ସମସ୍ତେ ଟିକେ ରାଜି ହୁଅନ୍ତି କି କଣ କୋପରେଟିଭ କରିକି ଟିକେ ଆନ୍ସର ଦିଅନ୍ତେ, ସେଇଟା ଟିକେ ମାନେ ଗୋଟେ ହେଲ୍ପଫୁଲ ହବ।
ହଁ ଯାଇକି ଜିନିଷଟା ଆମେ ସବମିଟ କରିଦେଲେ, ସମସ୍ତେ ଟିକେ ଦେଖା ଚାହାଁ ଟିକେ ହେଇଯାଆନ୍ତେ।
ହଁ
ଆଜ୍ଞା ଭଲ ହୁଅନ୍ତା ସେଇଟା
ନାଇଁ
ଟିକେ।
ସବମିଟ ଯାଇକିନା ସବମିଟ କରିବାଟା ବି ଗୋଟେ ପ୍ରକାର ପଜିଟିଭ ପଏଣ୍ଟ। କାହିଁକି ନା ଗୋଟେ ଆଡୁ କ୍ଲାରିଫାଇ ହେଇଯିବ ଯେ ଆମେ ଆମର ଇନଷ୍ଟିଚ୍ୟୁଟ ଟା ଆମେ ଦେଖିପାରିବା। ପ୍ଲସ
ହଁ
ତାର
ତାପରେ କିଛି
ଏନଭାରମେଣ୍ଟ ଆମେ
ଡାଉଟ
ବୁଲି
ଯଦି ବି
ପାରିବା।
ଥିବ ପଚାରି ପାରିବା ଜିନିଷଟା ଆମେ।
ହଁ ମାନେ ଆକ୍ୱେଣ୍ଟେଡ ହେବା ନା ସେଠିକାର ଲେକ୍ଚର ମାନଙ୍କ ସହିତ। ବାକି
ଆଜ୍ଞା
ଏନଭାରମେଣ୍ଟ ସହିତ ବି ଆମେ ଜାଣିବା। ଆଉ
ହଁ କେମିତି କଣ
ଆମେ
ପରୀକ୍ଷା ହଉଛି କି
ଷ୍ଟୁଡେଣ୍ଟ ମାନେ
ନାହିଁ।
ବି ମାନେ
ଆପଣ
କମ୍ୟୁନିକେଟ
ମାନଙ୍କର
କରିପାରିବା।
ଷ୍ଟଡି ସେଣ୍ଟର କୋଉଟା?
କେନ୍ଦ୍ରାପଡା
ଭୁବନେଶ୍ୱରରେ
କେନ୍ଦ୍ରାପଡା।
କେନ୍ଦ୍ରାପଡ଼ା ଅଟୋନମସ୍ କଲେଜ।
କେନ୍ଦ୍ରାପଡ଼ାକୁ?
ନା ନା
ହଁ
ରିଜନାଲ ସେଣ୍ଟର ହଉଛି ଭୁବନେଶ୍ୱର, ଷ୍ଟଡି ସେଣ୍ଟର ହଉଛି କେନ୍ଦ୍ରାପଡା।
ହଁ ଠିକ ଅଛି। ତାର ଅଲଗା କଣ ଗ୍ରୁପ କ୍ରିଏଟ ହେଇଛି କି? ଅଲଗା
ଅଭିଜିତ
ହଁ
ଆଙ୍କ ନମ୍ବର ନେଇକିନା ଟିକେ ଆଡ କରିଦିଅ।
ହଁ ହଁ ମୁଁ ତା ଲିଙ୍କ ଟା ପଠେଇ ଦଉଛି, ସେଇଠି ଜଏନ ହେଇଯିବେ।
ହଁ 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 ପଠେଇଦିଅ।
କୋଉଠି ଜିମେଲ ରେ ପଠେଇବେ?
ନାଇଁ
ନା
ନାଇଁ
ନା
ଏଇ ଏବେ ଯୋଉ ଏଇ ଯୋଉ ଚାଟ ର
ଏଇଠି
ମେସେଜ ରେ।
ଏଇଠି ପଠେଇଛି ରହିଥା।
ଏଠି କୋଉଠି ଶୋ ହଉଛି ମତେ ଜଣା ନାହିଁ ତ।
ନା
ଏଇଠି ଗୋଟେ
ପଠେଇତେ ପଡିବ
ଦେଖନ୍ତୁ ସବା
ଗ୍ରୁପକୁ
ତଳେ
ଯାଇକି
କଲ
ଇନଭାଇଟ
ପାଖରେ ଥ୍ରୀ
ଇନଭାଇଟ
ଡଟ
ଲିଙ୍କ
ଅଛି।
ଆଜ୍ଞା।
ଏବେ ଯୋଉ କଲ ଯୋଉ କାଟିବା ପାଇଁ ତା ସାଇଡ ରେ ଗୋଟେ ଥ୍ରୀ ଡଟ ଲାଇନ ରେ ନାହିଁ।
ହଁ ହଁ ହଁ।
ସେଇଠି ଗୋଟେ ଇନ କଲ ମେସେଜ ଅଛି ଦେଖନ୍ତୁ।
ଇନକଲ ମେସେଜ ମତେ ଶୋ
ତାକୁ କ୍ଲିକ
ହଉନି
କଲା
ତ।
ପରେ ଆପଣ କ୍ଲିକ କଲେ ସିନା ହବ।
କ୍ଲିକ୍ କଲା ପରେ ମ୍ୟୁଟ, ଡୋଣ୍ଟ ୱାଚ୍, ସ୍ପିନ୍, ରିମୁଭ୍, ଫୁଲ ସ୍କ୍ରିନ୍, କ୍ୟାନସେଲ ଏତିକି ହିଁ ଅପସନ ଶୋ
ନାଇଁ ନାଇଁ ନାଇଁ
ହଉଛି।
ସବା ତଳେ ଦେଖନ୍ତୁ ଗୋଟେ ସ୍କ୍ରିନ୍ ଅଛି, ଗୋଟେ ମାଇକ୍ରୋଫୋନ ଅଛି, ଗୋଟେ ସ୍ମାଇଲ ଅଛି। ତା ସାଇଡ ରେ ଗୋଟେ ଥ୍ରୀ ଡଟ ଅଛି।
ଓ ହଁ ହଁ ଠିକ ଅଛି ସେଇଠି।
ସେଇଠି ଇନ କଲ
ହଁ
ମେସେଜ
ହଁ
ଅଛି।
ହୁଁ ହୁଁ
ହଁ
ହୁଁ ହୁଁ।
ସେଇଥିରେ ଛାଡିଦେବେ।
ଓକେ ଠିକ ଅଛି।
ହୁଁ। ହଉ ଅଭିଜିତ ରହିଲି ତାହେଲେ।
ହଁ ହଁ ଟିକେ ସେଇ ଯୋଉ ଭଉଣୀ କହିଲେ ତାଙ୍କ ନମ୍ବର ଟା ନହେଲେ ଦିଅନ୍ତୁ ନା, ମୁଁ ଏବାଟେ ତ କାଇଁ ଲିଙ୍କ ଟା
ହଁ
ଆସୁନି।
ସେଇ ଇନକଲ ମେସେଜ ରେ ନିଜର ନମ୍ବର ଟା ଟିକେ ଲେଖିଦିଅ।
ଟିକେ ନମ୍ବର
ହଁ
ଟା ଲେଖିଦିଅନ୍ତୁ।
ହଁ ଲେଖି ଦଉଛି ମତେ ଏଡ
ହଁ
କରିଦିଅ।
ଟାଇପ କରିଦିଅ, ଟାଇପ କରିଦେଇକି ନିଜ ନାଁ ଟା ଲେଖିଦିଅ।
ନାଇଁ ମୁଁ ଲେଖିଦେଲି ମୋବାଇଲ ନମ୍ବର, ଟିକେ ପଠେଇ ଦିଅନ୍ତୁ।
ତମର ବାୟୋଲୋଜି ନା କଣ ମ୍ୟାଥମେଟିକ୍ସ?
ମୋର ମ୍ୟାଥମେଟିକ୍ସ ଫର କେମିଷ୍ଟ୍ରି।
ଆଚ୍ଛା ଆଚ୍ଛା ହଉ।
ଆପଣ ମାନଙ୍କର?
ଆମର
ଆମର
ବାୟୋଲୋଜି।
ବାୟୋଲୋଜି।
ଓହୋ।
ଏଇଟା
ହେଲା ନା
ହେଣ୍ଡ
ସୋ?
ଟୁ ହେଣ୍ଡ ସବମିଟ ଟା ସେପ୍ଟେମ୍ବର 30 ଭିତରେ କହିଛନ୍ତି। ଆଉ ପୋଷ୍ଟାଲ ଟା ଅକ୍ଟୋବର 15 ଭିତରେ କହିଛନ୍ତି, ନା 10 ଭିତରେ କହିଛନ୍ତି।
ଫୋନ ନମ୍ବର ସୋ ହେଲା ନା ସେଠି ନା ହେଲାନି?
ହଁ
ସୋ ହେଇଗଲା ସୋ ହେଇଗଲା।
କରୁଛି।
କେମିଷ୍ଟ୍ରି ଜେଏସ୍ ବୋଲି ଗୋଟେ ଗ୍ରୁପ ଆସିବ, ସେଇଥିରେ ଆଡ ହେଇଯିବେ।
ହଁ ଠିକ ଅଛି।
ତମ ଘର ଟା କୋଉଠି?
ମ୍ୟାଡାମ ଆପଣଙ୍କ ଗ୍ରୁପ ଟା ପ୍ରାଇଭେଟ ଅଛି କି ଆପଣଙ୍କ ହ୍ୱାଟସଆପ୍ ଟା? ହ୍ୟାଲୋ। ହ୍ୟାଲୋ।
ଏଡ ହେଲି।
ହଁ ଦେଖନ୍ତୁ ନା କେମିଷ୍ଟ୍ରି ଜୁଏଲ ସିଗ୍ନୁ।
ହଁ ହଁ ଏଡ ହେଲି।
ମ୍ୟାଡ଼ାମ ଆପଣଙ୍କ ଘରଟା କୋଉଠି?
ଆମର ଗଞ୍ଜାମ।
ଓହୋ।
ଗଞ୍ଜାମ ର କୋଉଠି?
ଦିଗ ପହଣ୍ଡି।
ଆଚ୍ଛା ଆଚ୍ଛା।
ଆପଣଙ୍କର?
ମୋର ମାଲକାନଗିରି, ସେପଟେ ବି ଟଚ୍ ଅଛି।
ଓହୋ।
ଆପଣଙ୍କର ଆସାଇନମେଣ୍ଟ ସରିଗଲାଣି ନା ମ୍ୟାଡ଼ାମ?
ନାଇଁ ଷ୍ଟାର୍ଟ କରିନି, ସେଇଟା ଯୋଉ 4 ସେଣ୍ଟିମିଟର ମାର୍ଜିନ ଛାଡ଼ିବା ପାଇଁ କହୁଛନ୍ତି, ବେଶୀ ହେଇଯିବନି? A4 ସାଇଜ
ଆମେ ତ
ପେପର
ଛାଡୁନୁ, ମୁଁ ତ 3 ପଟ ସାଇଡ ରୁ କରୁଛି। ମୁଁ 3 ପଟ ଦେଇକି ଯାହା ମଝିରେ ଲେଖିବା ଟା ଲେଖୁଛି।
4 ସେଣ୍ଟିମିଟର ଛାଡୁଛନ୍ତି କି ମାର୍ଜିନ?
ନା ନା,
ଆଜ୍ଞା।
ସେମିତି ସେଣ୍ଟିମିଟର ନାହିଁ। ମୁଁ ମନ ଇଚ୍ଛା ଇଏ କରି 3 ଆଡୁ
ନା ସେ
କରିଦଉଛି।
ପୁରା ନା ଭାଇ, ସେ ପୁରା ପ୍ରପର ଲେଖିଛନ୍ତି ଯେ ଇନଷ୍ଟ୍ରକ୍ସନ 4 ସେଣ୍ଟିମିଟର ଛାଡିବା ଉପର ତଳ ଆଉ ଲେଫ୍ଟ ସାଇଡ ରୁ।
ଉପର ତଳ ସିଏ କିଏ ଶୁଣୁଛି ସେଗୁଡାକ, ଆମେ ସେମିତି କରିକି ଦେଇ ଦଉଛୁ।
ହଁ ଦେଖିବେ, ଗୋଟେ ଏଇ ଯୋଉ ଛାଡିଥିଲେ ଗୋଟେ
ହଁ ନାଇଁ,
କ୍ୱେଶ୍ଚେନ ରେ।
ଇନଫରମେସନ ତ ଆସିଛି।
ଆଜ୍ଞା।
ଗ୍ରୁପରେ ଇନଫରମେସନ ଆସିଛି। 4 ମିଟର କୁଆଡେ ବା, 2 ସେଣ୍ଟିମିଟର କହୁଛନ୍ତି।
4 ସେଣ୍ଟି କହିଛନ୍ତି।
କାହିଁକିନା ଆସାଇନମେଣ୍ଟ କ୍ୱେଶ୍ଚେନ ଲେଖା ହେଇଛି 4 ସେଣ୍ଟିମିଟର ବୋଲି, ମୁଁ ଦେଖିଥିଲି।
ହଁ, 4
ସିଏ
ସେଣ୍ଟି ବେଶୀ ହେଇଯାଉଛି ନା।
କିନ୍ତୁ
ଏତେ ଗୁଡାକ
ଧରିଯିବ,
ପେପର
ମୁଁ ବି
ଲେଖିବା ପାଇଁ
ଲେଖିଛି
କଣ?
ମ୍ୟାଡାମ, ଧରିଯିବ ଧରିଯିବ। ଗୋଟେ ଗୋଟେ ପେଜରେ ଧରି ହଉଛି କ୍ୱେଶ୍ଚେନ ଆନ୍ସର। ଆଉ ପଛ ପଟରେ ଲେଖିବେନି, ଖାଲି ଫ୍ରଣ୍ଟ ପେଜ ଟା ଲେଖିବେ।
ହୁଁ।
ଓହୋ।
ପେଜରେ ଗୋଟେ ସାଇଡ ଲେଖିବେ, ଆଉ ଗୋଟେ ସାଇଡ ବ୍ଲାଙ୍କ ଛାଡିବେ।
ହୁଁ।
ମୁଁ ଏବେ କଲ କାଟିଲା ପରେ ମୁଁ PDF କରିକି ପଠେଇଦେବି ଯେ ମୁଁ କେମିତି କଣ ଲେଖୁଛି। ବାକି ମୁଁ
ମୋ
ସେମିତି 4-5 ସେଣ୍ଟିମିଟର ମୁଁ ଦେଖୁନି। ସେ
ସେମିତି
ଏତେ
କିଛି
ଧନ୍ଦା କିଏ
ମାଣ୍ଡାଟୋରି
କରୁଛି।
ନାହିଁ ପ୍ରାୟ, ନା କଣ?
ମୁଁ ଆଜିକାଲି ସେ ଯୋଉ ଅନଲାଇନରେ ଯୋଉ ଆସାଇନମେଣ୍ଟ ଗୁଡାକ ଯୋଉ ସବମିଟ କରୁନାହାନ୍ତି କି, ଯୋଉ ଆମକୁ ପୋଷ୍ଟାଲରେ ପଠଉଛନ୍ତି, ଯୋଉ ଆଜି କେତେ ହ୍ୱାଟ୍ସଆପ ଗ୍ରୁପ ରେ ସବୁ କରୁଛନ୍ତି, ମାନେ
ହଁ
ପଇସା
ହଁ
ଦିଅନ୍ତୁ ଆମେ ଆପଣଙ୍କୁ ସବମିଟ କରିଦବୁ, ଆପଣଙ୍କୁ ପୋଷ୍ଟାଲ କରିଦବୁ। ସେଗୁଡାକରେ ଦେଖିଲା ବେଳକୁ ତ କାହିଁ ସେମିତି କିଛି ନାହିଁ। ଆଉ
ନା ନା
ବାକି
ସେମିତି
ସବୁ କେତେ ଜଣ ବି ରୋଲିଂ ରେ ଲେଖୁଛନ୍ତି।
ଆଉ ତାପରେ ବି ଜଣେ ଜଣେ ବି ମାନେ ଗାର ପକା କାଗଜ ଲେଖି ଦଉଛନ୍ତି।
ହଁ, ମୁଁ କିନ୍ତୁ ମାନେ ହ୍ୱାଇଟ ପେପର, ମାନେ A4 ସାଇଜରେ ଲେଖୁଛି।
ହଁ, ମୁଁ ବି ସେଇ ଜେରକ୍ସ ପେପର ଯୋଉ ଗ୍ରୀନ କଲରରେ ସେଟା 70 GSM ରେ ସେଇଟାରୁ ଆଣିକି ଲେଖା ଷ୍ଟାର୍ଟ କରିଛି।
ହଁ, ମୋର ତ A4 ସାଇଜ ଆଉ ପେପର ହ୍ୱାଇଟ ପେପର ଆଉ।
ଆଜ୍ଞା।
ହଁ ହଁ, ଠିକ ଅଛି ଆଉ। ଏବେଠୁ ଲେଖା ଷ୍ଟାର୍ଟ କରିଦିଅ, ଲେଟ୍ କରନା। ବାକି ସମୟ ଅଭାବ।
ହଁ ହଁ, ସାରିଦବା ନିହାତି 15 ତାରିଖ ସୁଦ୍ଧା ସାରିଦବା, କାହିଁକିନା ଆଉ ତାପରେ
କାହିଁକି ନା ଅଗଷ୍ଟ ଆଜି ହେଇଗଲାଣି ନା। ପାଞ୍ଚ
ଆଜି
ଛଅ
4
ହେଇଗଲାଣି।
ତାରିଖ ହେଇଗଲାଣି।
ହଁ।
ଆଉ
ଆର
ତାପରେ
ମାସ
ସିଏ
ବେଳକୁ ତ ଏତିକି ବେଳକୁ ଖାଲି
ଯେଉଁମାନେ
ଅଗଷ୍ଟ
ୱେଷ୍ଟ
ଆସିବ।
ବେଙ୍ଗଲ ଅଛନ୍ତି, ସିଏ ତାଙ୍କର ପୁରା ମାନେ ସାଇଟ୍ ହେଇକି ରହିଛନ୍ତି। ସେମାନେ କିଛି କହିବାର ନାହିଁ, କିଛି ବୁଝିବାର ନାହିଁ।
ଅଧାରୁ ଅଧିକ ପିଲା ତ ସବୁ ଅନଲାଇନ ରେ ମଗେଇ ଦଉଛନ୍ତି, ନିଜ ନିଜ ପୋଷ୍ଟାଲ ରେ। ମାନେ ନିଜ ନିଜ ଆଡ୍ରେସରେ ମଗେଇ ଦଉଛନ୍ତି। ମାନେ
ଆଜ୍ଞା।
ଯୋଉ ଇଏ 3-4 ହଜାର ଟଙ୍କା ଦେଇକି ଯାହାର ଯେତେଟା ଆସାଇନମେଣ୍ଟ ଟୋଟାଲି ମଗେଇ ଦଉଛନ୍ତି।
ହଁ, ହ୍ୟାଣ୍ଡ ରିଟନ ଆସାଇନମେଣ୍ଟ ଆସି ମଗେଇ ଦଉଛନ୍ତି ଡାଇରେକ୍ଟ ଇଏରୁ।
ହଁ ବା।
ଆଉ ତାପରେ ଆପଣ ଏଇ ଯୋଉ ମାନେ କେମିତି ସିଲେଇ କରୁଛନ୍ତି, ତାକୁ ମାନେ ବାନ୍ଧୁଛନ୍ତି କେମିତିକା?
ନା ନା, ମୁଁ ଏ ଯାଏ ବାନ୍ଧିନି। ମାନେ ଏମିତି କରିକି ରଖିଛି, ଦୋକାନକୁ ଯାଇକି ତାକୁ ବଡ ଷ୍ଟେପଲରରେ ମାରି ଦେଇକି, ଏ ଯୋଉ ମୋଟା ମାନେ ଟିକେ ବଡ ସେଲୋ ଟେପ ନାଇଁ କି, ତାକୁ
ହଁ ହଁ,
ଇଏ କରିଦେବି
ସେମିତି ବି
ଦେଇଦେବି।
କରିବେ, ନହେଲେ ଏଇ ଯୋଉ ଆମର ନାହିଁ କି କଣା କରିବା ପାଇଁ ଯୋଉ ମେସିନ୍।
ହଁ, କଣା କରିକି ଯୋଉ ସ୍ପାଇରାଲ ବାଣ୍ଡିଂ।
ଆଜ୍ଞା ଆଜ୍ଞା,
ସୂତାରେ
ସେଇଗୁଡା ବି କରିକି ଦେଇପାରିବେ।
ହଁ। ସେଇଟା ଗୋଟେ ଡିଜାଇନ ଆଉ, ନହେଲେ କଣ ଆଉ, ମାନେ ନିଜ ପାଖେ ତ ରହିବନି ନା ଏତିକି ସବୁ। ଆମର ପଇସା ଖର୍ଚ୍ଚ କରିକିନା ତାଙ୍କ ମାନଙ୍କୁ ଦେବାର ଅଛି।
ହଁ ହଁ ହଁ।
ପୁଣି ସେଇଠି ଗଲା ପରେ ଗୋଟେ ପାଲା, ସେମାନେ କହିବେ କି ଏଇଟା ଆପଣଙ୍କର ଠିକ ହେଇଛି, ଏଇଟା ଆପଣଙ୍କର ଭୁଲ ହେଇଛି।
ହଁ ହଁ, ସେଇଥିପାଇଁ ସେଇଟା ମାନେ ପ୍ରପର ଭଲିକି ବୁଝିକି, ନହେଲେ ମୁଁ ପ୍ରାୟତଃ ଭାବୁଛି ସେ ରିଜନାଲ ସେଣ୍ଟରକୁ ଫୋନ କରି ପଚାରିକି ଜାଣିତେ ପଡିବ ଯେ ଜିନିଷ ଟା କେମିତି କଣ ସାର୍ ଦେଲେ
ମୁଁ
ଠିକ ହବ।
ଏବେକୁ ପାଖାପାଖି 3-4ଟା ମେଲ ଆସିଲାଣି। ସେଇ ମେଲ ତଳେ ଯେତିକି ନମ୍ବର ଅଛି ସେମାନଙ୍କୁ ମେସେଜ କଲିଣି। ଇଭେନ ଆମର ଯୋଉ କୋଅର୍ଡିନେଟର ଅଛନ୍ତି ପ୍ରଭାତ କୁମାର ମଲ୍ଲିକ ନା ପ୍ରସନ୍ନ କୁମାର ମଲ୍ଲିକ ସମଥିଙ୍ଗ, ଯିଏ ଯୋଉ
ଆଜ୍ଞା।
ମେସେଜ ଛାଡୁଛନ୍ତି, ସେମାନଙ୍କୁ ତାଙ୍କୁ ମେସେଜ କଲା ବେଳକୁ ସିଏ ଜଣେ 2 ଜଣଙ୍କର ନାଁ ମେନସନ କଲେ। ତାଙ୍କୁ ମୁଁ ଜଣେଇଲି, ସାର୍ ମୁଁ ଏମିତି ଏମିତି ଏଇ ପ୍ରକାର ରିଜନାଲ ସେଣ୍ଟର, ମୋ ନାଁ ଏଇଆ ଷ୍ଟୁଡେଣ୍ଟ। ଆଉ ଆସାଇନମେଣ୍ଟ କଣ ଇଏ ସେ ପ୍ରସଙ୍ଗରେ ଗଲା ବେଳକୁ ଗୋଟେ ବି ରିପ୍ଲାଏ ନାହିଁ। ଇଭେନ ମୁଁ ପ୍ରଭାତ ସାରଙ୍କୁ ମେସେଜ କଲି କି ସାର୍ ମୁଁ କେବେଠୁ ଆପଣଙ୍କୁ ମେସେଜ କରୁଛି, ବାରମ୍ବାର ମୁଁ ଆପଣଙ୍କୁ ଇଏ କହୁଛି, ଆପଣଙ୍କ ତରଫରୁ ଗୋଟେ ବି ରିପ୍ଲାଏ ଆସୁନି। କଣ ଚାଲିଛି, ଏମିତି କହିଲାରୁ ବି ତଥାପି ରିପ୍ଲାଏ ଆସୁନି।
ଓହୋ, ଆପଣ ଗୋଟେ କାମ କରନ୍ତୁ, ସେଠି ଆମର ଦେଖିବେ ହଉଛି ଷ୍ଟଡି ସେଣ୍ଟର ର ଅଛି ନମ୍ବର 2-3ଟା ଅଛି।
ଆଉ
ତାଙ୍କ
ଗୋଟେ
ଯେତେବେଳେ
ଅଭିଜିତ ମାର୍କ କରିଥିବ, ଆମର ଜେନେରାଲ ଫିଜିକାଲ କେମିଷ୍ଟ୍ରି ଯୋଉ ଜ୍ୟୋତି ସାର୍ ଯୋଉ ପଢଉଛନ୍ତି, ଧଳ
ଆଜ୍ଞା
ସାର୍।
ଆଜ୍ଞା।
3ଟା କ୍ଲାସ ନେଲେ, 120 ନା 150ଟା ପେଜ ଶେଷ। 3ଟା
ହଁ
କ୍ଲାସ।
ତାପରେ ତ
ମାନେ
ମ୍ୟାଡାମ ବି
ପିଲା
ଆଜି
କଣ
ଟିକେ ଯାହା
ପଢୁଛନ୍ତି କଣ
ପଢେଇଲେ
ନାହିଁ।
ସଂସେ 4ଟା ମାନେ 4ଟା ୟୁନିଟ୍ ଦିଟା କ୍ଲାସ ରେ ଶେଷ।
ନାଇଁ 3ଟା କ୍ଲାସ ହେଇଛି, 3ଟା ନା 4ଟା ହେଇଛି, ପରେ ଯୋଉ
ହଁ
ଏକ୍ସଟ୍ରା ନେଇଥିଲେ।
4ଟାରୁ ମ୍ୟାଡାମଙ୍କର 2ଟା ହେଇଛି, ସେ ଧଳ ସାରଙ୍କର 2ଟା ହେଇଛି।
ହଁ।
ଆଉ ଗୋଟେ ଆମେ ସମସ୍ତେ ମିସ୍ କରିଯାଇଥିଲେ ଆମର 27 ତାରିଖ ଯୋଉ ହେଇଥିଲା ଷ୍ଟାର୍ଟିଂ ଟା, ସେଇଟା କୌଣସି
ହଁ
ଆମର ମିସ୍ ହେଇଥିଲା।
ହଁ ଯୋଉଟା
ଆଉ
ବି ହଉ
ବର୍ତ୍ତମାନ
ଆସିକି
ବର୍ତ୍ତମାନ
140 ନା 150ଟା ପେଜ ଛାଡିଲେଣି, ମାନେ ଦେଖିକି ପଢଉଛନ୍ତି ମାନେ ଲାଇନ ବାଇ ଲାଇନ।
ହଁ କେବଳ ତ ଲାଇନ ବାଇ ଲାଇନ, ଦେଖାଯାଉ କଣ ହଉଛି, ନିଜେ ହିଁ ପଢିତେ ପଡିବ, ସେଲ୍ଫ ଷ୍ଟଡି ନ କଲେ ହବନି ଏଇ ଜିନିଷରେ। ଆଉ
ସମୟ
ଦେଖାଯାଉ
କାଇଁ,
କଣ ଆଉ
ଆମେ
ବର୍ତ୍ତମାନ ଆପଣ
କାଲି
କଣ
ସକାଳୁ
କରୁଛନ୍ତି?
ମନେକର ଆମେ କାଲି ଆସାଇନମେଣ୍ଟ ସବମିଶନ କରିଥିବା, ତାର 15-20 ଦିନ ପରେ ଡେଟ୍ ବାହାର କରିଦେବେ, ଆସ ପ୍ରାକ୍ଟିକାଲ ପାଇଁ। ପ୍ରାକ୍ଟିକାଲ ସାରିକି ଘରେ ଟିକେ ଶାନ୍ତିରେ ବସିଥିବା କି ନାଇଁ, ତାର 20-25 ଦିନ ପରେ ଆସ ଏକ୍ଜାମ ହଲକୁ ଆସ।
ହଁ ସିଏ
ପ୍ରାକ୍ଟିକାଲ ପାଇଁ
ପ୍ରାୟତଃ
ଆମକୁ
ସେଇ ଡିସେମ୍ବରରେ
କେନ୍ଦ୍ରାପଡା
କରିଦେବେ
ଯିବାକୁ
ଏକ୍ସାମ।
ପଡିବ।
କଣ ହେଇଛି
ପ୍ରାକ୍ଟିକାଲ ଏ ପାଖାପାଖି ହବ ନା ଆମକୁ କେନ୍ଦ୍ରାପଡା ଯିବାକୁ ପଡିବ?
ନା ଭୁବନେଶ୍ୱରରେ ହବ।
ସେଇଟା ଜଣେଇବେ, ମେସେଜରେ ଜଣେଇବେ,
ସେଇଟା
ସବୁ
ଜଣା
ଜିନିଷ ତ
ପଡିନି, ସେଇଟା ଗ୍ରୁପରେ
ଇନଫରମେସନ
ମେସେଜ
ସେୟାର
କରିବେ ଗୋଟେ
କରୁଛନ୍ତି।
ଅଫିସିଆଲି।
ଓହୋ ହଉ ଠିକ ଅଛି।
ଏବେ ଖାଲି
ଆପଣ
ଆସାଇନମେଣ୍ଟ କୁ ଧ୍ୟାନ ଦିଅ, ଆଉ କିଛି ନାହିଁ।
ଆପଣ ଭାଇ କିନା କଣ କରୁଛନ୍ତି ବର୍ତ୍ତମାନ?
ଆଁ
ଆପଣ ବର୍ତ୍ତମାନ କଣ କରୁଛନ୍ତି?
ମୋର ତ ଏବେକୁ 2ଟା ଆସାଇନମେଣ୍ଟ ସରିଲାଣି, ଥାର୍ଡ ମାନେ ଗୋଟେ ଆଉ ଗୋଟେ ତୃତୀୟ ନମ୍ବର ଆସାଇନମେଣ୍ଟ ର 2 ନମ୍ବର ଚାଲିଛି।
ଓହୋ ନା ନା ମାନେ ମୁଁ କଣ କହୁଥିଲି କି, ମାନେ ଆପଣ ଜବ୍ ହେଇଆ କରୁଛନ୍ତି ନା କଣ?
ନା ନା ଭାଇ ମୁଁ ଷ୍ଟୁଡେଣ୍ଟ ଅଛି, ମୋର ମୁଁ ବିଇଡି ସାରିଲି 2024ରେ ସାରିଲି। ଆଉ ଓଏସଟି କ୍ଲିୟର ଅଛି, ବାକି ଚାଲିଛି କମ୍ପିଟେଟିଭ ଦଉଛି।
ଆଜ୍ଞା।
SBI, RRB, UPSC, OPSC ସବୁ କମ୍ପିଟେଟିଭ ପାଇଁ ପ୍ରିପେୟାର ହଉଛି।
ଏଇଥର ଯୋଉ ବାହାରିଛି ଗୋଟେ ଇଣ୍ଟେଲିଜେନ୍ସ ବ୍ୟୁରୋ ର ପକେଇଛନ୍ତି ନା ପକେଇନାହାନ୍ତି?
ହଁ ହଁ 650 ଟଙ୍କା ନେଇଯାଇଛନ୍ତି ଆମଠୁ।
ଆଜ୍ଞା ଆଉ ଗୋଟେ 10 କ୍ଲାସ୍ ଲେବୁଲ ର ବି ବାହାରିଛି।
ନା ନା
ଆଉ
ମୁଁ
ପିଓ ଟା ତ
ପକେଇନି
ମୁଁ
ସେଇଟା।
ପକେଇନି। IBPS ପିଓ ଟା ପକେଇନି, କ୍ଲର୍କ ଟା ଦେଖିବା ଏଇଥର ତ ବାହାରିଛି ନା କଣ
ମୁଁ
ପକେଇବି।
ଗଲା ବେଳକୁ ଏଇ ଯୋଉ ଆମର ସରସ୍ଵତୀ ପୂଜା ନା କେବେ ଗୋଟେ ଏଇ ଯୋଉ କଣ ସେଟା ଗଲା, ଏ ଯୋଉ ଶିବରାତ୍ରି ବୋଧେ ଗଲା।
ଆଜ୍ଞା।
ସେତେବେଳକୁ IBPS ପିଓ, IBPS କ୍ଲର୍କ ବାହାରି ନଥିଲା କି, ସେଇଟା
ହଁ
ପକେଇଥିଲି।
ହଁ
ହଁ ସେଇଟା ମୁଁ ଦେଇଥିଲି, ବାକି ହେଲାନି ମୋର।
ଓହୋ ହଉ
ଏମିତି
ଦେଖିବା
ଆଉ।
ଯାହାଟା ହଉଛି ପକାନ୍ତୁ ପକାନ୍ତୁ ଠାକୁରଙ୍କ ଦୟାରୁ।
ହୁଁ ଏବେ ଏଇଠି ଆଗକୁ OCS ଟା ଆସୁଛି, ସିଭିଲ ସର୍ଭିସ ଟା।
ଓହୋ ଆପଣ କୋଚିଂ ନଉଛନ୍ତି ନା କୋଉଠି, ନା କେମିତି କଣ?
ନା ନା ମୁଁ ଭୁବନେଶ୍ୱରରେ କୋଚିଂ ନଉଥିଲି, ଗଲା ଦୀପାବଳି ବେଳକୁ ଛାଡିଲି। ଘରକୁ ପଳେଇ ଆସିଲି,
ଓହୋ
ନହେଲେ
କେତେ
ପାଖାପାଖି 2.5
କେତେ
ବର୍ଷ
କଣ
ଥିଲା
ନେଲେ
ଏଇଠି।
ବର୍ଷକୁ କେତେ କଣ ନେଲେ?
ମୋର ବର୍ଷକୁ ନେଇଥିଲେ 24,000 ନେଇଥିଲେ କମ୍ପିଟେଟିଭ ପାଇଁ। ତା ବାଦ ମୁଁ
ଆଜ୍ଞା
70,000 ଟଙ୍କା ଦେଇଥିଲି ବିଇଡି ପାଇଁ। ପ୍ଲସ ବାଣିକରେ ମୁଁ ଆକ୍ଚୁଆଲି କରୁଥିଲି। ମୋର ବାଣିଜ୍ୟରେ ବିଇଡି, ମୋର ବାଣିଜ୍ୟରେ କୋଚିଂ ଆଉ ବାଣିଜ୍ୟରେ PGDCA।
ଓହୋ ନା ବାଣିଜ୍ୟ ଟା ଭଲ, ବର୍ତ୍ତମାନ ବାଣିଜ୍ୟ ଟା ଚାଲିଛି ସିଓର ସକ୍ସେସ୍।
ନାଇଁ ବାଣିଜ୍ୟ ଟା ଭଲ, ବାକି କମ୍ପିଟେଟିଭ ପାଇଁ, ଅନ୍ୟ ପାଇଁ କିଛି ନାହିଁ।
ଶିବୁର ଖୋର୍ଦ୍ଧାରେ ପଡିଥିଲା, ଖୋର୍ଦ୍ଧାରେ ପରୀକ୍ଷା ପଡିଥିଲା।
ଆମର ହଉଛି ବା ଆମର କଣ କହୁଥିଲେ କହୁଥିଲା ଆପଣ ଯୋଉ ନେଲେ ଓଏସ୍ ପାଇଁ ନେଲେ ନା କଣ?
କୋଉଟା ଯୋଉ UPSC ଯୋଉ OPSC ଟା?
ଆଜ୍ଞା ଆଜ୍ଞା।
ନାଇଁ ନାଇଁ ଯୋଉ କୋଚିଂ ଟା ତ, କୋଚିଂ ଟା
ହଁ
ମୋର
ହଁ କୋଚିଂ
OSSC ଆଉ OSSS ଆଉ ଆମର ଇଏ ପାଇଁ SSC।
SSC ପାଇଁ ଆଜ୍ଞା।
ରେଲୱେ SSC ଆଉ ରେଲୱେ ପାଇଁ।
ଆଜ୍ଞା।
ବ୍ୟାଙ୍କିଙ୍ଗ ପାଇଁ ନେଇ ନଥିଲି, ବାକି ସବୁ ଆଡକୁ
ଓହୋ
ପକଉଛି ଦେଖାଯାଉ। ଘରେ ଥାଇକି ବି ପ୍ରିପେୟାର ହଉଛି।
ହଁ ହଁ ଦେଖିବା ଯାହା ହଉ ଠାକୁରଙ୍କ ଦୟାରୁ।
ହଁ
ହଉ ହଉ
ଏମିତିରେ ତ ହେଇ 26 ହେଇଗଲାଣି ଆମକୁ, ଆଉ କଣ ଆହୁରି ଅଛି।
ଆଜ୍ଞା ଆଜ୍ଞା ନିହାତି।
ତମକୁ କେତେ କଣ ହେଲାଣି?
ମୋର 22 ବର୍ଷ ଆଜ୍ଞା।
ଓହୋ ହେଲା ଆଉ,
ଏଇ
ଏଇ ସବୁ
ଆଜ୍ଞା
ଭେଟ ବାଟ ହବା। କିଏ 2 ବର୍ଷ, କିଏ ବର୍ଷେ, କିଏ
ହଁ
ସମାନ,
ଏଟା ତ ବଡ ସାନ ଅଛି ଆଉ
ଏମିତି
ଜିନିଷ
ସବୁ ହେଇକିନା ଅଛି ଆଉ।
ଆଜ୍ଞା ହଉ ଭାଇ
ଠିକ ଅଛି।
ରହିଲେ ଆଜ୍ଞା।
ହଁ ହଁ
ଗୁଡ୍ ନାଇଟ୍।
ହଁ ଭାଇ ଗୁଡ଼